Since the dawn of human consciousness, we have gazed at the stars and wondered about the true nature of time. The concept of time travel has woven itself deeply into the fabric of human imagination, appearing in ancient myths, folklore, and religious texts, long before science gave us reason to believe it might be possible. From H.G. Wells' groundbreaking novel, The Time Machine, published in 1895, to modern blockbusters like Interstellar, Avengers: Endgame, and Tenet, the allure of breaking free from time's linear constraints continues to captivate us. But why does this concept hold such power over our collective imagination? Perhaps it's because time itself remains one of the greatest mysteries we face. We experience it constantly, yet cannot touch it, stop it, or naturally manipulate it. We are bound by its arrow, always moving forward, never backward. The ability to transcend this fundamental limitation represents one of humanity's most profound fantasies. Ancient civilizations pondered time's mysteries in their own ways. The Mayans developed sophisticated calendars that track celestial movements across vast time periods, while Hindu cosmology envisioned cosmic cycles spanning billions of years. The ancient Greeks had two concepts of time: chronos, the sequential, measurable time we track with clocks, and kairos, the qualitative, right moment, or opportune time. These distinctions show how deeply humans have always contemplated time's nature. Even before Einstein revolutionized our understanding of physics, philosophers questioned whether time was absolute or relative. Immanuel Kant argued that time was not an objective feature of reality, but a structure imposed by human perception. Henri Bergson distinguished between clock time and experience time, how moments can stretch or compress in our subjective experience. These philosophical inquiries foreshadowed scientific revelations that would come later. In fiction, time travel takes many forms. Sometimes it's a gleaming machine with spinning dials and flashing lights. Other times, it's a cosmic accident or a quirk of advanced technology. Stories like Back to the Future explore the paradoxes and complications that would arise if we could alter our own past. Doctor Who imagines time as a vast playground for adventure and exploration. Dark and 12 Monkeys examine predestination and the cyclical nature of causality. These narratives don't just entertain us, they challenge our understanding of reality itself. The appeal of time travel fiction reveals much about our psychology. Stories of going back in time often center on fixing mistakes or preventing tragedies, reflecting our universal wish for second chances. Tales of journeying to the future typically explore our anxieties and hopes about where humanity is headed. And time loop stories like Groundhog Day or Russian Doll provide metaphors for personal growth and transformation, learning from repeated experiences until we become better versions of ourselves. Eastern philosophical traditions have their own perspectives on time. Buddhist thought sees time as cyclical rather than linear, with reincarnation allowing consciousness to experience many lifetimes. Taoism emphasizes being present in the eternal now rather than dwelling on past or future. These perspectives remind us that our Western conception of time as an arrow moving only forward isn't the only way to conceptualize temporal existence. Yet there's a profound difference between fictional time travel and what modern physics suggests might be possible. In movies, time travelers often maintain complete control over their destination and return journey. They retain their memories and physical form. The timeline either changes dramatically or splits into multiple realities. But the actual science of potential time travel paints a much stranger, more constrained picture. Einstein's theories suggest that time is not absolute but relative, flowing at different rates depending on gravity and velocity. This isn't the convenient time travel of fiction, but it is a genuine form of time manipulation observed in the natural world. Consider the GPS satellites orbiting Earth. They experience time slightly faster than we do on the planet's surface due to weaker gravitational effects, without accounting for this time difference, amounting to microseconds per day. Our entire global positioning system would rapidly become useless. This isn't science fiction, it's operational science happening right now, proving that time's flow is malleable. The science of time began to transform dramatically in the early 20th century. In 1905, a young patent clerk named Albert Einstein published his special theory of relativity, which proved that time isn't absolute, but depends on the relative motion between observers. If two perfectly synchronized clocks are separated, with one remaining stationary and the other accelerating to near light speed before returning, they will show different times. The moving clock will have experienced less time than the stationary one. This isn't a measurement error or mechanical failure, it's a fundamental property of time itself. Einstein expanded on these ideas 10 years later with his general theory of relativity, which described gravity not as a force, but as a curvature of space-time caused by mass and energy. This theory predicted that massive objects like stars and planets would not only bend space but slow the passage of time in their vicinity. The stronger the gravitational field, the more pronounced this time dilation would be. These predictions have been verified with extreme precision through experiments involving atomic clocks at different altitudes and astronomical observations. When we contemplate time travel, most of us imagine journeying backward to witness historic events or prevent personal tragedies. The desire to revisit the past runs deep in human consciousness. We yearn to correct mistakes, to experience moments of significance with the wisdom we now possess, or simply to witness history unfolding through our own eyes. This longing has inspired countless works of art, from Kurt Vonnegut's Slaughterhouse-Five, where the protagonist becomes unstuck in time, to James Cameron's Terminator franchise, which explores whether the future is predetermined or can be rewritten. The most poignant aspect of our relationship with time might be how it connects to mortality. Our awareness of our finite existence, that our time is limited, creates both existential dread and gives meaning to our lives. Time travel fantasies often represent a refusal to accept these limitations, a dream of cheating death by stepping outside time's normal flow. In some sense, time travel serves as a secular version of the religious promise of eternal life. But the physics of backward time travel presents profound challenges. Causality, the principle that causes must precede their effects, forms a cornerstone of our understanding of reality. Violating this principle introduces paradoxes that seem logically impossible to resolve. The most famous is the grandfather paradox. If you traveled back in time and prevented your grandfather from meeting your grandmother, you would never be born. But if you were never born, how could you travel back in time to interfere with their meeting? Such circular reasoning creates logical loops that defy our understanding of cause and effect. The grandfather paradox has variants that appear throughout time travel fiction. In Back to the Future, Marty McFly must ensure his parents fall in love after accidentally interfering with their first meeting, or he'll cease to exist. A more complex version appears in stories like 12 Monkeys, where attempts to prevent a catastrophe become part of the chain of events leading to that very catastrophe. These narratives highlight the logical conundrums inherent in backward time travel. Some theoretical physicists have proposed solutions to these paradoxes. The many worlds interpretation suggests that traveling back in time might create a new timeline or branch in reality, leaving the original timeline intact. Others propose that the universe might somehow self-correct, making it physically impossible to create a paradox no matter how hard you try. Your attempts to change history would always fail in some way, preserving the consistency of space-time. The physicist Igor Novikov formulated the self-consistency principle, arguing that any attempt to create a paradox would be prevented by the laws of physics themselves. Events would conspire to prevent logical contradictions, perhaps through improbable coincidences. Science fiction sometimes explores this idea, showing time travelers whose attempts to change the past accidentally cause the very events they were trying to prevent, creating a closed causal loop. While backward time travel remains deeply problematic, forward time travel, at least in limited form, is not just possible but proven. Einstein's special relativity demonstrated that as an object approaches the speed of light, time slows down relative to stationary observers. This effect, called time dilation, has been verified countless times in laboratory settings. Atomic clocks placed on high-speed aircraft return slightly behind their stationary counterparts. Particles in accelerators experience dramatic time dilation as they approach light speed. The famous twin paradox thought experiment illustrates this principle. If one twin remains on Earth while the other takes a journey at near light speed, the traveling twin would return younger than the Earthbound sibling. The difference wouldn't be merely subjective, it would be physically measurable in every cell of their bodies, in every radioactive atom, in every physical process. The traveler would have experienced less time than the stay-at-home twin. If we could build a spacecraft capable of traveling at 99.5% the speed of light, far beyond our current technological capabilities, a 5-year journey for the crew would correspond to roughly 50 years passing on Earth. Upon return, the travelers would have effectively journeyed 45 years into Earth's future. This isn't bending the rules of physics, it's using them exactly as Einstein described. Science fiction has explored these relativistic effects in works like Joe Haldeman's The Forever War, where soldiers fighting a distant interstellar conflict return to an Earth centuries more advanced than when they left due to time dilation. The emotional impact of such displacement, losing everyone you've ever known to time's passage while barely aging yourself, highlights both the wonders and the personal tragedies that could accompany even scientifically plausible time travel. But what about more dramatic forms of time travel? Could we ever move through time more directly, without spending subjective years in transit? This is where black holes enter our story. These cosmic monsters represent the most extreme warping of space-time we know of in the universe. Near a black hole, time slows dramatically compared to distant observers. Fall too close, and you cross a boundary called the event horizon, beyond which even light cannot escape. What happens to time itself beyond this cosmic threshold? Black holes have captured the public imagination almost as much as time travel itself. These regions of space where gravity becomes so strong that nothing can escape their pull represent the ultimate cosmic mystery. First predicted by Einstein's general theory of relativity in 1915, black holes remained theoretical constructs for decades. Even Einstein himself was skeptical about their physical reality. It wasn't until the 1960s and 1970s that astronomical observations began to provide compelling evidence for their existence. The term black hole wasn't coined until 1967 by American physicist John Wheeler, though the concept had been studied mathematically since the 1910s. The first black hole candidates were identified in the 1970s through observations of X-ray emissions from binary star systems, where a normal star orbits an invisible companion whose gravitational effects suggest an object too dense to be anything other than a black hole. Today, we know that black holes are common throughout the universe. Supermassive black holes lurk at the centers of most galaxies, including our own Milky Way, where Sagittarius A star, a black hole with the mass of approximately 4 million suns, silently shapes the orbits of nearby stars. Smaller stellar mass black holes form from the collapsed cores of massive stars that have exhausted their nuclear fuel. These cosmic corpses continue to influence their surroundings through their immense gravitational pull, sometimes revealing themselves when they feed on gas from companion stars or merge with other black holes, generating ripples in space-time called gravitational waves. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, the supermassive black hole at the center of Galaxy M87. This remarkable achievement, requiring a virtual telescope the size of Earth, through coordinated observations from multiple radio telescopes around the world, provided visual confirmation of these extraordinary objects. The image showed exactly what Einstein's equations had predicted a century earlier: a dark central region surrounded by a bright ring of light bent by the black hole's gravity. The defining feature of a black hole is its event horizon, a boundary in space-time beyond which events cannot affect an outside observer. Once something crosses this threshold, its fate is sealed. It will inevitably be drawn toward the center of the black hole, where our current physics predicts a singularity, a point of infinite density where the known laws of physics break down entirely. This prediction of a singularity is one reason physicists believe our current theories are incomplete. nature may abhor infinities as much as physics does. Some theoretical physicists have proposed that black holes might be more than just dead ends in space-time. They might connect to other regions of our universe, or even other universes entirely, through theoretical tunnels called wormholes. If such connections exist and could somehow be traversed, might they offer paths not just through space, but through time as well? The mathematics of Einstein's equations permits such possibilities. At least in theory, black holes represent such extreme conditions that they push our understanding of physics to its breaking point, creating a natural laboratory for exploring the deepest questions about the nature of time itself. Stephen Hawking once remarked that black holes are where God divided by zero, a metaphor for how these objects represent singularities where our equations break down and new physics might emerge. When we look at a black hole from afar, we're seeing an object so massive that it creates a depression in the fabric of space-time, like a bowling ball placed on a trampoline. But this simple analogy fails to capture the true strangeness of what happens near and within these cosmic behemoths. As you approach a black hole, space becomes increasingly curved and time increasingly distorted. Minutes for you might translate to years for someone watching from a safe distance. This dramatic stretching of time, called gravitational time dilation, is not just theoretical. We've measured it in less extreme environments, confirming Einstein's predictions. Black holes simply take this phenomenon to its ultimate extreme. If you could hover just outside a black hole's event horizon without falling in, a practically impossible feat, you would witness the entire future history of the distant universe unfold before your eyes in a matter of hours. In a very real sense, you would be traveling into the future. The movie Interstellar dramatically illustrated this effect in the scene where astronauts visit a planet orbiting near a supermassive black hole. Every hour on the planet corresponded to 7 years passing back on Earth. While the film took some creative liberties, this basic relativistic effect was scientifically accurate and based on the calculations of physicist Kip Thorne, who served as scientific consultant and executive producer. But could black holes offer a path to the past as well? This is where the science becomes more speculative, but no less fascinating. Certain solutions to Einstein's equations, like the Kerr metric describing rotating black holes, suggest the theoretical possibility of closed time-like curves, paths through space-time that return to their starting point not just in space, but in time as well. In essence, a loop through time. The mathematics of general relativity doesn't explicitly forbid such possibilities. In 1949, the mathematician Kurt Gödel, a close friend of Einstein, discovered a solution to Einstein's equations that described a rotating universe in which closed time-like curves could exist, allowing for the theoretical possibility of backward time travel. Einstein himself was troubled by this finding, as it seemed to challenge basic notions of causality. If the past could be altered, how could we make sense of cause and effect? Einstein reportedly told Gödel that his own equations kept him awake at night, worrying about the implications of a universe where past and future might not be clearly separated. This conversation between two of history's greatest minds highlights how deeply challenging the concepts of time travel are, even for those who best understood the mathematics behind them. In the decades since Gödel's discovery, other theoretical scenarios involving extreme warping of spacetime have been proposed that might permit backward time travel. These include traversable wormholes, theoretical tunnels through spacetime that could connect distant regions of the universe or even different points in time. While Einstein's equations permit wormholes, keeping them open would require exotic matter with negative energy, something we've never observed naturally in the universe. The physicist Kip Thorne and his colleagues published influential papers in the late 1980s, exploring the theoretical possibility of traversable wormholes. They calculated that maintaining an open wormhole would require a form of matter with negative energy density, what physicists call exotic matter. While quantum physics allows for small, brief manifestations of negative energy through phenomena like the Casimir effect, Producing and stabilizing enough exotic matter to maintain a traversable wormhole remains far beyond our capabilities. Another speculative possibility involves cosmic strings, theoretical defects in space-time left over from the early universe. If two such strings were to pass close to each other at near light speed, they might create a region where closed time-like curves could exist. Similarly, a rapidly rotating cylinder of incredibly dense material, sometimes called a Tipler cylinder, after physicist Frank Tipler, might create conditions where space-time becomes so twisted that paths leading backward in time could theoretically form. These scenarios all share common challenges. They would require either cosmic objects we've never observed, materials with properties that might be physically impossible, or energy requirements far beyond anything our civilization could muster. And they all potentially introduce those troubling causality paradoxes that seem to defy logical resolution. Yet the history of science teaches us humility. Many concepts now fundamental to our understanding of reality, from heliocentrism to quantum uncertainty, were once considered impossible or absurd. Our intuitions evolved from a world of moderate sizes, speeds, and energies. When we venture into the extremes, the very fast, the very massive, the very small, our intuitions often fail us. The universe proves stranger than we imagined. The physicist Richard Feynman once remarked, "I think I can safely say that nobody understands quantum mechanics." The quantum realm, with its superposition, entanglement, and probabilistic nature, demonstrates how reality at its most fundamental level defies our common sense expectations. If quantum mechanics teaches us anything, it's that the universe is not obligated to conform to our intuitive understanding. The challenges to realizing time travel possibilities are immense. The physics required might demand exotic forms of matter with negative energy, something we've never observed naturally. The energies involved would dwarf our most powerful technologies by countless orders of magnitude. And fundamental principles like causality, the relationship between cause and effect, might ultimately forbid such journeys. Yet the universe has surprised us before. Quantum mechanics revealed a subatomic realm that defies our intuitive understanding of reality. Black holes themselves were once considered mathematical curiosities rather than real objects, until astronomical observations proved their existence. The intersection of quantum effects and extreme gravity might reveal new possibilities we cannot yet imagine. The search for a unified theory of quantum gravity, reconciling Einstein's relativity with quantum mechanics, represents one of the greatest challenges in modern physics. Such a theory would be essential for understanding what happens at the center of black holes or during the first moments of the Big Bang. It might also clarify whether closed time-like curves can actually exist, or if some yet undiscovered principle forbids them. Popular culture continues to explore these themes, often serving as a gateway for public interest in complex physics. Christopher Nolan's film Interstellar, developed in consultation with theoretical physicist Kip Thorne, portrayed gravitational time dilation with unprecedented scientific accuracy. The hero's journey near a supermassive black hole results in decades passing on Earth, while only hours elapse for him, a dramatization of actual relativistic effects. Our fascination with time travel reflects something profound about human nature. We are the only species on Earth that contemplates its past and future with such depth and abstraction. We alone feel the weight of history and responsibility toward future generations. Perhaps our desire to transcend time's constraints speaks to our awareness of our own mortality, our limited time in the universe, and our yearning to experience more than one lifetime allows. There's a certain poetic resonance between our quest to understand time and the cosmos itself. The light from distant galaxies brings us images from the ancient past due to the finite speed of light. When we observe a galaxy 8 billion light-years away, we're seeing it as it existed 8 billion years ago, a natural form of looking back in time. Astronomy is, in a very real sense, a study of history written in light. As we peer deeper into the cosmos with instruments like the Event Horizon Telescope which captured the first direct image of a black hole's shadow, we edge closer to understanding these mysterious objects. Each new observation and theoretical breakthrough brings us one step closer to answering the ultimate question: does the fabric of reality itself permit journeys through time? Or are we forever bound to experience it one moment at a time, in one direction only? To truly explore whether time travel through black holes is possible, we must first understand what these cosmic entities really are. Let's delve deeper into the nature of black holes, objects so extreme they represent the boundaries of physics itself, and explore how they might hold the key to time's deepest secrets. Black holes stand as perhaps the most enigmatic objects in our universe, regions of space where gravity's pull is so intense that nothing, not even light itself, can escape once it crosses a boundary known as the event horizon. To understand these cosmic monsters fully, we must begin with their birth, for black holes are not primordial features of the universe, but rather the spectacular endpoints in the life cycles of certain stars. Stars begin their lives as vast clouds of hydrogen gas that slowly collapse under their own gravitational attraction. As these clouds contract, they heat up, eventually igniting nuclear fusion in their cores. This fusion generates an outward pressure that counterbalances gravity's inward pull, creating a delicate equilibrium that can last for billions of years. Our own sun currently exists in this stable phase and will continue to do so for approximately another 5 billion years. But stars do not burn forever. Eventually, they exhaust their nuclear fuel. What happens next depends critically on the star's mass. Small stars like our sun will shed their outer layers, forming beautiful planetary nebulae, while their cores contract to become white dwarfs, dense, Earth-sized remnants that slowly cool over trillions of years. But for stars with masses at least 8 times greater than our sun, a far more dramatic fate awaits. When these massive stars exhaust their hydrogen fuel, they begin fusing heavier elements, first helium, then carbon, oxygen, silicon, and finally iron. But iron fusion consumes rather than releases energy, disrupting the star's delicate balance. Within seconds, the star's core collapses, triggering a catastrophic explosion known as a supernova, among the most energetic events in the universe, briefly outshining entire galaxies of billions of stars. The fate of the stellar remnant following this explosion depends on its mass. If the core's mass is between about 1.4 and 3 solar masses, it will collapse into a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons on Earth. But if the core's mass exceeds about 3 solar masses, not even the pressure of neutrons can halt the collapse. Gravity overwhelms all known forces in nature, and the star's core continues to contract without limit, forming a singularity, a point of effectively infinite density where our current laws of physics break down completely. Surrounding this singularity is the event horizon, forming what we call a black hole. The term black hole itself was coined relatively recently, in 1967, by American physicist John Wheeler, though the theoretical foundations for these objects date back to 1916, just after Einstein published his general theory of relativity. Karl Schwarzschild, a German physicist and astronomer, found an exact solution to Einstein's complex field equations, describing the space-time around a perfectly spherical mass. This solution predicted that if matter were compressed sufficiently, it would create a region from which nothing could escape, what we now call a black hole. For decades, black holes remained mathematical curiosities rather than observed phenomena. Even Einstein himself was skeptical about their physical reality, but gradually, evidence accumulated. In 1972, astronomers discovered Cygnus X1, a powerful source of X-rays that appeared to be coming from an invisible object orbiting a blue, supergiant star. The invisible object's estimated mass, about 15 times that of our Sun, suggested it could only be a black hole. Today, astronomers have identified numerous stellar mass black holes throughout our galaxy, typically by observing their effects on companion stars or the radiation emitted by matter falling toward them. But stellar mass black holes, while remarkable, are not the most massive black holes in the universe. At the centers of most large galaxies, including our own Milky Way, lurk supermassive black holes with masses millions or even billions of times greater than our Sun. The black hole at the center of our galaxy, Sagittarius A star, pronounced Sagittarius A star, has a mass equivalent to about 4 million suns compressed into a region smaller than our solar system. How these supermassive behemoths formed remains one of astronomy's greatest mysteries. They may have grown from stellar mass black holes that merged and consumed vast quantities of matter over billions of years. Alternatively, they might have formed directly from the collapse of enormous clouds of gas during the early universe. Or perhaps they arose through some combination of these processes. Regardless of their origin, these cosmic giants shape the evolution of their host galaxies, influencing star formation and galactic structure through their immense gravitational influence. Between stellar mass black holes and supermassive black holes, astronomers have recently begun to find evidence for an intermediate category, imaginatively called intermediate mass black holes, with masses hundreds to thousands of times that of our Sun. These middleweights might represent crucial stepping stones in the formation of their supermassive cousins, though conclusive evidence for their existence has proven elusive until recently. Despite their diverse origins and masses, all black holes share certain fundamental features. Perhaps the most important is the event horizon, the boundary marking the point of no return. The event horizon isn't a physical surface, but rather a region in space-time where the escape velocity exceeds the speed of light. Since nothing can travel faster than light, a cosmic speed limit built into the fabric of our universe, anything crossing this boundary can never escape. The radius of the event horizon, known as the Schwarzschild radius, depends directly on the black hole's mass. For a black hole with the mass of our Sun, this radius would be just 3 kilometers. For the supermassive black hole at our galaxy's center, it's about 12 million kilometers, roughly 17 solar radii. Despite their potentially enormous masses, black holes can be remarkably compact. Contrary to popular imagination, a black hole isn't a cosmic vacuum cleaner indiscriminately sucking in everything around it. If our Sun were magically replaced by a black hole of identical mass, Earth's orbit would remain unchanged. We would freeze rather than be pulled in, as the gravitational field at this distance would be exactly the same as before. Black holes are dangerous only when you get close, very close. As you approach a black hole, you would experience tidal forces, differences in gravitational pull between your feet and head if you were falling feet first. For very massive black holes, you might cross the event horizon without noticing anything dramatic, as these tidal forces would be relatively mild at the horizon. But for smaller black holes, tidal forces near the event horizon become catastrophically strong, stretching your body vertically while compressing it horizontally, a process gruesomely but accurately termed spaghettification. What lies beyond the event horizon remains theoretically contentious. Classical general relativity predicts a singularity at the center, a point of infinite density and infinitely curved space-time. But most physicists believe this mathematical infinity signals the breakdown of general relativity rather than representing physical reality. A complete theory of quantum gravity, which would unify Einstein's relativity with quantum mechanics, might eliminate these infinities and reveal the true nature of a black hole's interior. While we cannot see beyond the event horizon, black holes are not necessarily invisible. Matter falling toward a black hole forms an accretion disk, a flattened band of gas and dust spiraling inward like water circling a drain. As this material accelerates and compresses, it heats to millions of degrees, emitting enormous amounts of radiation across the electromagnetic spectrum before crossing the event horizon. Some of the most luminous objects in the universe are quasars, distant, active galactic nuclei powered by supermassive black holes devouring matter at prodigious rates. In 2019, astronomy reached a watershed moment with the first direct image of a black hole's shadow, the dark region where light is captured by the event horizon, surrounded by the bright glow of the accretion disk. This remarkable achievement by the Event Horizon Telescope collaboration, which linked radio telescopes across the globe to create a virtual Earth-sized telescope, targeted the supermassive black hole at the center of Galaxy M87, located 55 million light-years from Earth. The image showed exactly what Einstein's equations had predicted a century earlier: a dark central region surrounded by a bright, asymmetrical ring of light, its shape distorted by the black hole's extreme gravity bending the path of light itself. Another way to detect black holes emerged in 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves, ripples in space-time predicted by Einstein a century earlier. These particular waves were generated by two black holes, each about 30 times the mass of our Sun, spiraling together and merging into a single, more massive black hole. This observation not only confirmed another prediction of general relativity, but opened an entirely new window for observing the universe through gravitational, rather than electromagnetic radiation. The relationship between black holes and time forms the core of our exploration. Einstein's general relativity revealed that gravity not only curves space, but also slows time. The stronger the gravitational field, the more pronounced this effect becomes. Near a black hole, where gravity reaches extremes found nowhere else in the universe, time dilation becomes dramatic. If you could hover near the event horizon of a black hole, while your friend remained at a safe distance, you would experience time passing normally from your perspective. But if you could somehow communicate with your distant friend, you would discover that for every minute you experienced, much more time, hours, days, or even years, had passed for them. This isn't science fiction. It's a direct prediction of general relativity that has been verified in less extreme environments. Atomic clocks placed at different altitudes tick at measurably different rates due to Earth's gravitational field. GPS satellites must correct for these time differences to provide accurate positioning. Black holes simply take this phenomenon to its ultimate extreme. If you were to fall into a black hole, crossing the event horizon would not seem momentous from your perspective. You would continue to experience time moving forward normally, but to an outside observer watching you fall, ignoring for the moment the practical challenges of actually seeing someone cross the horizon, you would appear to slow down as you approach the horizon, moving ever more sluggishly, eventually seeming to freeze at the boundary. Any light emitted from your position would be increasingly redshifted, stretched to longer, redder wavelengths, eventually becoming too faint to detect. You would fade from view without ever being seen to cross the horizon, at least from the external observer's perspective. This strange relativistic effect highlights a profound aspect of black holes. They represent regions where our usual notions of space and time break down. The event horizon marks not just a boundary in space, but a horizon in time as well. What lies beyond is, in a very real sense, the future, a region from which no information can ever return to influence the past. But what about the singularity, that theorized point of infinite density at a black hole's center? Here, our mathematics suggests something even stranger. In the simplest black hole solutions to Einstein's equations, non-rotating, spherically symmetric black holes, known as Schwarzschild black holes, the singularity represents not just a point in space, but a moment in time. As you fall deeper into such a black hole, the radial direction effectively becomes temporal rather than spatial. Moving toward the singularity becomes as inevitable as moving forward in time. There is no standing still any more than we can pause the flow of time in normal circumstances. Reality, however, is likely more complex. Actual black holes rotate, inheriting the angular momentum of the matter that formed them. These rotating black holes, described by the Kerr metric, named after New Zealand mathematician Roy Kerr, exhibit even more exotic properties. Their singularities are not points but rings, and their space-time structure potentially allows for closed time-like curves, paths through space-time that, if traversable, could theoretically permit backward time travel. Of course, tremendous practical and theoretical barriers would prevent any actual use of black holes as time machines. The extreme conditions near a black hole would destroy any conventional matter or life form. Even if some advanced technology could somehow protect a traveler, the energy requirements and engineering challenges would be astronomical. And fundamental principles like causality, the relationship between cause and effect, might ultimately forbid such journeys, preventing the paradoxes that would arise if the past could be altered. Nevertheless, black holes provide a natural laboratory for exploring the most extreme predictions of general relativity. They represent regions where space-time becomes so warped that our intuitive notions of before and after, here and there, lose their usual meanings. Understanding black holes means grappling with the true nature of space and time themselves. Adding further intrigue to black holes is their relationship with quantum mechanics. In the 1970s, Stephen Hawking made the revolutionary discovery that black holes aren't entirely black. Quantum effects near the event horizon cause black holes to emit radiation, now called Hawking radiation. This process gradually reduces the mass of the black hole, meaning that over enormously long timescales, far longer than the current age of the universe for stellar mass black holes eventually evaporate. This quantum behavior led to the infamous black hole information paradox, a profound conflict between general relativity, which suggests information falling into a black hole is lost forever, and quantum mechanics, which maintains that information cannot be destroyed. This ongoing theoretical puzzle has driven some of the most important work in theoretical physics over the past decades, potentially providing a window into a unified theory of quantum gravity. Black holes also play a central role in speculative theories about wormholes, hypothetical tunnels through space-time that could connect distant regions of our universe or even different universes entirely. Einstein's equations permit such connections, at least mathematically, though keeping them open would require exotic forms of matter with negative energy, something we've never observed naturally in substantial quantities. If traversable wormholes could somehow exist and remain stable, they might theoretically allow for shortcuts not just through space, but potentially through time as well. But like many aspects of black hole physics, the gap between mathematical possibility and physical reality remains vast. The energy requirements and physical laws might ultimately prevent such exotic scenarios from ever being realized. Nevertheless, the study of black holes continues to advance our understanding of fundamental physics. Each new observation, from gravitational wave detections to direct imaging, provides fresh insights and tests the predictions of our theories with ever greater precision. The recent detection of gravitational waves from merging black holes has opened an entirely new window into these dark cosmic objects, allowing us to hear their collisions through the vibrations they create in space-time itself. In April 2019, the Event Horizon Telescope collaboration unveiled the first direct image of a black hole's shadow, capturing the supermassive black hole at the center of Galaxy M87. This remarkable achievement marked the culmination of years of technical development and international cooperation. The image showed exactly what Einstein's equations had predicted: a dark central region where light is captured by the black hole, surrounded by a bright ring formed by photons orbiting the black hole before escaping toward our telescopes. This visual confirmation of black holes' existence and structure represented one of the most significant astronomical achievements of the century. Looking ahead, future observations promise to reveal even more about these cosmic enigmas. The Event Horizon Telescope continues to improve its capabilities and has now imaged Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. Space-based gravitational wave detectors like the planned Laser Interferometer Space Antenna, LISA, will detect mergers of supermassive black holes across the universe, providing unprecedented insights into how galaxies and their central black holes evolve together. As we peer deeper into these mysterious objects with increasingly sophisticated instruments, we edge closer to understanding their true nature, and perhaps by extension, the fundamental nature of space, time, and gravity themselves. Black holes represent nature's most extreme laboratory, pushing our theories to their limits and beyond. In their unfathomable depths may lie keys to a deeper understanding of reality itself. Having explored the nature and behavior of black holes, we can now turn our attention to one of their most fascinating aspects: how they affect time. The extreme warping of space-time near black holes creates conditions where time itself flows at dramatically different rates, a phenomenon known as time dilation. This relativistic effect, while present throughout the universe, reaches its most extreme manifestation in the vicinity of these cosmic behemoths. Let's explore how black holes distort the very fabric of time and what this might mean for the possibility of time travel. To understand how black holes might offer a pathway to time travel, we must first grasp one of the most profound revelations of modern physics: time is not absolute. This seemingly simple statement represents a radical departure from our intuitive understanding of reality, where time seems to flow uniformly for everyone, everywhere. Yet Einstein's theories of relativity revealed that time's passage depends on motion and gravity, with extraordinary implications for objects near black holes. Before Einstein, scientists and philosophers viewed time as Newton described it: absolute, true, and mathematical, flowing uniformly without reference to anything external. In this classical view, time served as the universal backdrop against which all events played out. Every properly functioning clock, regardless of its location or motion, would tick at precisely the same rate. Time was seen as entirely independent of the physical world it contained. Einstein's 1905 special theory of relativity shattered this conception. He demonstrated that time's flow depends on relative motion between observers. If you're moving very fast relative to me, time passes more slowly for you from my perspective. This isn't an illusion or measurement error. It reflects the actual nature of time itself. Einstein unified time and space into a single entity called spacetime, where neither time nor space exists as an absolute independent dimension. 10 years later, Einstein expanded these insights with his general theory of relativity, which revealed that gravity isn't a force pulling objects together, but rather a curvature of spacetime caused by mass and energy. Massive objects like stars and planets bend the fabric of spacetime around them, creating what we experience as gravitational attraction. This same warping affects time's passage. Near massive objects, time flows more slowly than in regions of weaker gravity, a phenomenon called gravitational time dilation. Both forms of time dilation, from motion and from gravity, have been verified with extraordinary precision. In 1971, physicists placed extremely accurate atomic clocks on commercial airliners and flew them around the world, then compared them with identical clocks that remained stationary on Earth. The moving clocks recorded slightly less elapsed time, exactly as Einstein's theories predicted. Today, the Global Positioning System, GPS, must continuously adjust for both special and general relativistic effects to maintain accuracy. Without accounting for time flowing slightly faster on orbiting satellites than on Earth's surface, GPS navigation would accumulate errors of about 10 kilometers per day. These everyday examples involve tiny time differences, nanoseconds and microseconds. But as we approach environments with extreme gravity or near light speeds, time dilation becomes dramatically more pronounced. Near a black hole, where space-time curvature reaches its maximum possible value, these effects reach truly mind-bending proportions. Imagine two twins, one remaining on Earth while the other travels to orbit a supermassive black hole, like the one at the center of our galaxy, Sagittarius A star. The traveling twin establishes an orbit carefully calibrated to avoid falling into the black hole, while remaining close enough to experience significant time dilation. From the Earth-bound twin's perspective, watching through an impossibly powerful telescope, the orbiting twin would appear to move in slow motion. Every gesture, every movement would seem dramatically slowed. If they could somehow communicate, the Earth-bound twin might experience decades passing, while the spacefaring twin experienced only months or even days. This isn't merely theoretical speculation, but a direct consequence of Einstein's equations that govern spacetime. In 2020, astronomers observed a star called S2, orbiting very close to our galaxy's central black hole. By measuring the light from this star as it passed through the intense gravitational field near Sagittarius, a star, they detected the gravitational redshift predicted by general relativity. Direct evidence of time dilation in action near a black hole. The closer one gets to a black hole's event horizon, the more extreme this time dilation becomes. At the horizon itself, time as experienced by an outside observer appears to stop completely. If we could somehow watch an object falling toward a black hole, we would never actually see it cross the event horizon. Instead, the object would appear to slow down more and more, becoming increasingly redshifted, its light stretched to longer, redder wavelengths by the extreme gravitational field, eventually fading from view. From our external perspective, the falling object would seem frozen at the horizon for eternity. Yet, from the perspective of someone falling into a black hole, nothing unusual would happen when crossing the event horizon. Time would continue to flow normally, and the horizon itself has no physical manifestation, no surface, no barrier, nothing to mark this point of no return except the impossibility of ever sending a signal back to the outside universe. The infalling observer would continue falling toward the center, experiencing an increasingly intense gravitational field until reaching the singularity at the black hole's core. This asymmetry of perspectives, time stopping from the outside view while continuing normally for the falling observer, highlights a profound aspect of Einstein's relativity, the relativity of simultaneity. Events that appear simultaneous from one reference frame may occur at different times when viewed from another. Near a black hole, this relativity becomes so extreme that what constitutes now becomes entirely dependent on the observer's position and motion. The most dramatic form of time dilation would occur if one could somehow hover just outside a black hole's event horizon, an incredibly difficult feat requiring enormous energy to counteract the black hole's gravitational pull. In this scenario, time would pass normally for the hovering observer, but the outside universe would appear to evolve at an accelerated rate. Looking outward with a powerful telescope, they might watch stars live and die in what seemed like minutes. Galaxies evolve over what felt like days. In a very real sense, the hovering observer would be traveling into the distant future of the external universe. The 2014 film Interstellar dramatically illustrated this concept with its depiction of a planet orbiting near a supermassive black hole called Gargantua. Every hour spent on the planet's surface corresponded to 7 years passing on Earth. While the film took creative liberties with certain aspects of black hole physics, this time dilation effect was based on accurate science, with equations provided by theoretical physicist Kip Thorne, who served as the film's scientific consultant. Thorne's calculations showed that a planet could theoretically experience such dramatic time dilation if it orbited at just the right distance from a rapidly spinning, supermassive black hole. This relationship between black holes and time reveals a possible pathway for one-way time travel into the future. If we could somehow harness black holes for this purpose, perhaps by establishing stable orbits or stations near their event horizons, we might create conditions where explorers could effectively jump forward in time relative to the outside universe. Spending subjective years near a black hole might correspond to centuries or millennia passing elsewhere. Of course, the practical challenges would be enormous. The intense gravitational fields near black holes create extreme tidal forces that would tear apart conventional spacecraft long before reaching the necessary proximity to the event horizon. Even if we could somehow engineer vessels capable of withstanding these forces, the energy requirements for maintaining position or orbit so close to a black hole would be astronomical. And perhaps most significantly, this would be a one-way journey. The time travelers could move forward into the future, but never return to their original time. For those interested in traveling backward in time, the prospects seem even more challenging. However, certain theoretical solutions to Einstein's equations suggest intriguing possibilities. In 1949, mathematician Kurt Gödel discovered a solution describing a rotating universe containing closed time-like curves. paths through space-time that return to their starting point in time as well as space. If one could follow such a curve, one would return before one's departure, effectively traveling backward in time. While our universe doesn't match Gödel's model, rotating black holes described by the Kerr metric, named after mathematician Roy Kerr, might theoretically contain similar, closed, time-like curves. The mathematics suggests that inside the event horizon of a rotating black hole, particularly in a region called the ergosphere, space-time becomes so twisted that paths looping backward in time might exist. Following such a path could, in principle, allow for backward time travel. The challenges of utilizing such a mechanism would be even more formidable than those for forward time travel. First, one would need to cross the event horizon, which is traditionally a one-way journey. Even if one could somehow survive this crossing and follow a closed, time-like curve, there's no known way to exit the black hole and return to the outside universe. The physics required might demand what scientists call exotic matter, material with negative energy density that could theoretically stabilize wormholes connecting different regions of space-time. While quantum field theory permits small amounts of negative energy density in localized regions, we've never observed the quantities that would be needed for macroscopic applications like time machines. Moreover, many physicists propose that even if the mathematics allows for closed time-like curves, some yet undiscovered principle of physics, sometimes called the chronology protection conjecture, proposed by Stephen Hawking, might prevent backward time travel to avoid the paradoxes it would create. The universe might fundamentally enforce causality, ensuring that causes always precede their effects. Despite these theoretical possibilities, current understanding suggests that black holes alone cannot serve as practical time machines in either direction. However, they might form components of more complex structures that could theoretically allow for time travel. Wormholes. Wormholes, or Einstein-Rosen bridges, are hypothetical tunnels connecting separate points in space-time. First proposed as a solution to Einstein's field equations in 1935 by Einstein himself and physicist Nathan Rosen, wormholes would theoretically create shortcuts through space-time. Most wormhole solutions are extremely unstable, collapsing instantly if any matter attempts to pass through them. However, in 1988, physicists Michael Morris, Kip Thorne, and Ulva Yurtsever proposed that a wormhole could theoretically be held open using exotic matter with negative energy. If such a traversable wormhole could be created or found naturally, and if one end were placed near a black hole or accelerated to relativistic speeds, the two ends would experience different time dilations. After sufficient time passed, the ends would connect points not just in space but in time as well. Entering one mouth of the wormhole might allow exit through the other mouth at an earlier time, effectively creating a time machine. The relationship between wormholes and black holes remains an area of active theoretical research. Some physicists have suggested that black holes and wormholes might be intimately connected, perhaps even different manifestations of the same fundamental structure. However, most wormhole theories require exotic matter to prevent collapse, while black holes can form naturally from collapsing stars without requiring any exotic components. The quest to understand black holes and their relationship to time draws upon multiple branches of physics, bringing together Einstein's general relativity with quantum mechanics, two frameworks that have proved remarkably difficult to reconcile. In regions of extreme gravity, like near black holes, both theories make predictions, yet they often contradict each other. This conflict has driven theoretical physics for decades, spawning attempts at unified theories like string theory and loop quantum gravity. One of the most perplexing aspects of black hole physics emerged from Stephen Hawking's work in the 1970s. Applying quantum field theory to the region near a black hole's event horizon, Hawking discovered that black holes should emit radiation, now called Hawking radiation. This process would cause black holes to lose mass slowly and eventually evaporate completely. For stellar mass black holes, This evaporation would take longer than the current age of the universe by many orders of magnitude, but the theoretical implications are profound. Hawking's discovery led to the infamous black hole information paradox. Quantum mechanics insists that information cannot be destroyed, yet a black hole seems to erase the details of whatever falls into it, leaving only mass, charge, and angular momentum. When the black hole eventually evaporates through Hawking radiation, where does this information go? This question has sparked decades of theoretical work and remains unresolved, though recent developments suggest that information might be preserved in subtle quantum correlations in the Hawking radiation itself. This intersection of quantum mechanics and black hole physics might ultimately illuminate new possibilities for understanding time itself. Some approaches to quantum gravity suggest that space-time might not be fundamental but emergent, arising from deeper quantum processes. In such theories, our conventional understanding of time as a smooth, flowing dimension might be merely an approximation of a more granular reality, similar to how water appears as a continuous fluid, despite being composed of discrete molecules. As we continue to study black holes through observations, experiments, and theoretical work, we edge closer to understanding these enigmatic objects and their relationship to the fabric of reality. The Event Horizon Telescope's first image of a black hole shadow in 2019 provided stunning confirmation of Einstein's century-old predictions. Future observations promise even greater insights, perhaps eventually revealing clues about the nature of time itself. For now, black holes serve as cosmic laboratories for testing our most fundamental theories about space, time, and gravity, while practical time travel through black holes remains firmly in the realm of speculation rather than engineering. The physics of time dilation near these cosmic behemoths is well-established science. Every observation of matter orbiting close to a black hole, every detection of gravitational waves from black hole mergers, every simulation running on supercomputers helps us refine our understanding of how these objects distort the very fabric of space-time around them. Our fascination with black holes and time travel reflects something profound about human nature. Our desire to transcend limitations, to explore beyond boundaries, to understand the universe on its most fundamental level. As we peer into the darkness of these cosmic giants, we also look inward, questioning our place in a universe where time itself proves more fluid than our ancestors ever imagined. Time dilation near black holes reminds us that our everyday experience of time represents just one perspective in a universe of possibilities. What we perceive as rigid and universal, the steady flow of seconds, minutes, and hours, reveals itself as relative and malleable when viewed through the lens of Einstein's theories. This realization doesn't just change our understanding of black holes, it transforms our conception of reality itself. Having explored how black holes affect time from a safe distance, we can now turn our attention to an even more extreme question. What would happen if we ventured beyond the event horizon? What would a journey into a black hole reveal about the nature of space, time, and perhaps even the possibility of time travel? Let's examine the physics of falling into these cosmic abysses and what such a journey might entail. Having explored black holes from a theoretical perspective and examined how they distort time from a distance, we now approach a more radical question. What would happen if we actually ventured beyond the event horizon? While such a journey would be fatal in reality, thought experiments about falling into black holes have provided profound insights into the nature of space, time, and gravity. Let's embark on this one-way journey, if only in our imaginations, to understand what black holes might reveal about the possibility of time travel. Our journey begins far from the black hole, where space-time is only slightly curved by its gravitational field. At this distance, everything seems normal. The black hole appears as a dark sphere against the backdrop of stars, its presence revealed primarily by its gravitational effects on surrounding matter and light. As we accelerate toward this cosmic abyss, we begin to notice subtle changes in our perception of the universe around us. The first effect we would observe is gravitational lensing. The black hole's immense gravity bends light passing near it, distorting our view of background stars and galaxies. Stars that should be hidden behind the black hole become visible as their light curves around it. The cosmic backdrop begins to warp, with images of distant objects appearing in multiple places simultaneously. This isn't an optical illusion, but the actual bending of light's path through curved space-time, one of the first predictions of Einstein's general relativity confirmed by astronomical observations. As we draw closer, the black hole no longer appears as a simple dark sphere. Instead, we observe a complex pattern of light and shadow. The black region in the center, the event horizon itself, is surrounded by a bright photon ring formed by light that orbits the black hole multiple times before escaping toward our eyes. This pattern closely matches what the Event Horizon Telescope captured in its groundbreaking 2019 image of the supermassive black hole at the center of galaxy M87. Behind us, the universe begins to appear increasingly compressed into a shrinking circle of light. This optical effect occurs because the black hole's gravity bends light from all directions toward our line of sight, concentrating our view of the entire universe behind us into an ever-narrowing region. Meanwhile, in front of us, the black hole's silhouette grows larger, eventually dominating our field of view. As we continue our approach, we experience the first signs of tidal forces, the difference in gravitational pull between the parts of our spacecraft closer to and farther from the black hole. These forces stretch us vertically while compressing us horizontally, a phenomenon colorfully termed spaghettification by physicist Stephen Hawking. For a stellar mass black hole, these tidal forces would become lethal long before reaching the event horizon, literally tearing apart any physical object atom by atom. However, for supermassive black holes like those at the centers of galaxies, the tidal forces at the event horizon are much milder. The larger the black hole, the less extreme the gravitational gradient at its horizon. For a black hole with millions or billions of solar masses, you could theoretically cross the event horizon without experiencing catastrophic tidal forces. This counterintuitive fact emerges from the mathematics of general relativity. While the total gravitational pull increases with mass, the difference in gravitational pull across a fixed distance decreases for larger black holes. This distinction between stellar mass and supermassive black holes proves crucial for our thought experiment. To have any hope of surviving long enough to cross an event horizon, even theoretically, we must choose a supermassive black hole as our destination. So let's imagine our journey continues towards Sagittarius, a star, the 4 million solar mass black hole at the center of our Milky Way galaxy. As we approach this behemoth, we encounter another relativistic effect, time dilation. Our clocks appear to run normally from our perspective, but communication with distant observers reveals an astonishing discrepancy. For every hour we experience on our inward journey, much more time passes for observers watching from a safe distance. This effect becomes increasingly pronounced as we draw closer to the event horizon. If we could somehow maintain a hovering position near the event horizon, requiring enormous energy to counteract the black hole's gravitational pull, we would become unwitting time travelers. Watching the distant universe through our telescopes, we would see events unfolding at an accelerated pace. Stars would race through their life cycles, galaxies would evolve before our eyes, and cosmic history would unfold rapidly while we experienced only minutes or hours of subjective time. This dramatic time dilation illustrates how black holes naturally create conditions for one-way time travel into the future. The closer we hover to the event horizon, the further into the future we can witness, though we can never return to our original time. This isn't speculative science fiction, but a direct consequence of Einstein's equations that has been indirectly confirmed through multiple experiments and observations. But what happens when we finally cross the event horizon itself? From our perspective inside the falling spacecraft, nothing dramatic occurs at this boundary. There's no physical barrier, no sudden change in forces, no alarm that sounds when we cross this one-way membrane in space-time. The event horizon isn't a material surface, but a mathematical boundary defined by escape velocity. We would pass through it without any local indication that we had reached a point of no return. This seamless crossing contradicts the common portrayal of event horizons as violent, turbulent boundaries. The apparent contradiction arises from the dramatically different perspectives of the falling observer versus distant witnesses. To those watching from afar, we would appear to slow down as we approach the horizon, eventually freezing at the boundary, never quite crossing it. Our image would gradually redshift and fade from view as the light we emit struggles increasingly to climb out of the black hole's gravitational well. But from our perspective falling inward, we cross the horizon in a finite amount of our experienced time. Once across, the truly strange aspects of black hole interiors begin to manifest. The most profound change involves the roles of space and time themselves. Inside the event horizon, the radial direction toward the singularity takes on temporal rather than spatial characteristics. Moving toward the central singularity becomes as inevitable as moving forward in time. Just as we cannot choose to stop the flow of time or move backward in time under normal circumstances, inside the event horizon, we cannot stop our inward motion toward the singularity. The experience would be disorienting in ways difficult to comprehend. Our perception of space would fundamentally change. If we looked outward, away from the singularity, we would still see the external universe, but compressed into an increasingly small patch of our visual field. Light from the outside universe would continue to reach us, highly blue-shifted due to our inward acceleration. Meanwhile, looking inward toward the singularity, we would see nothing. No light can travel outward from deeper regions to reach our eyes. It's not darkness in the conventional sense, but rather an absence of any visual information whatsoever. A void more absolute than any darkness we can imagine. The mathematician Roger Penrose illustrated this bizarre rearrangement of space-time with diagrams showing how light cones, the paths available to particles moving at light speed, tip over inside the event horizon. Outside the horizon, future light cones contain directions leading both toward and away from the black hole. Inside the horizon, all future directions point toward the singularity. The black hole's gravitational field becomes so intense that space and time effectively exchange roles. How long would we survive after crossing the horizon? For a supermassive black hole like Sagittarius A star, we might have minutes or even hours of experienced time before reaching the central singularity, depending on our trajectory. But our fate is sealed. Every path leads to the same destination, the singularity at the black hole's center, where tidal forces become infinite, and our current physics breaks down completely. This inevitable journey toward the singularity highlights a crucial point about black holes and time travel. While black holes dramatically affect the flow of time, they don't naturally provide mechanisms for returning to the past. At least that's the case for non-rotating, spherically symmetric black holes described by the Schwarzschild metric. However, real black holes rotate. They inherit angular momentum from the matter that formed them and from subsequently consumed material. These rotating black holes, described mathematically by the Kerr metric, named after New Zealand mathematician Roy Kerr, have even more exotic properties than their non-rotating counterparts. The space-time inside a rotating black hole differs significantly from the Schwarzschild case. Instead of a point singularity, rotating black holes contain a ring singularity. More importantly for our exploration of time travel, the mathematics of the Kerr metric suggest the theoretical possibility of closed time-like curves, paths through space-time that return to their starting point in time as well as space. Following such a path could, in principle, allow for backward time travel. This possibility arises from how rotation affects space-time. A rapidly spinning black hole drags the fabric of space-time around it in a process called frame dragging, creating a region called the ergosphere, where space itself rotates. Inside certain regions of a maximally rotating black hole, this frame dragging becomes so extreme that paths can theoretically loop back on themselves temporally. The physicist Kip Thorne, whose work on wormholes and time travel inspired the film Interstellar, has extensively studied these theoretical possibilities. While the mathematics allows for such closed time-like curves, Thorne and others have identified numerous barriers to actually utilizing them for time travel. The extreme conditions near singularities would destroy any conventional matter. Quantum effects, not accounted for in classical general relativity, might prevent the formation of closed time-like curves. And even if such paths exist and could somehow be traversed, there's no known way to exit the black hole afterward to utilize this time travel capability. Thorne's scientific contributions to this field extend beyond mere theoretical speculation. His work with students and colleagues led to specific predictions about the properties of wormholes and time machines that might be constructed using black holes. These calculations revealed that any time machine based on general relativity would need to obey certain rules. Most importantly, no time machine can be created that would allow travel back to a time before the machine itself was built. This chronology protection principle suggests fundamental limitations on backward time travel, even if the basic physics allowed for it. The film Interstellar drew heavily on Thorne's scientific expertise, particularly in its depiction of the supermassive black hole Gargantua and the relativistic effects experienced by characters who ventured near it. The dramatic time dilation depicted in the film, where 1 hour on a planet orbiting near the black hole corresponded to 7 years passing on Earth, was based on accurate calculations performed by Thorne specifically for the film. The visual depiction of the black hole itself, with its asymmetric accretion disk and gravitational lensing effects, set new standards for scientific accuracy in science fiction cinema. While the film took creative liberties with certain plot elements, particularly regarding the black hole's interior, its portrayal of relativistic effects like time dilation and gravitational lensing represents one of the most scientifically informed depictions of black hole physics in popular culture. Some theorists have proposed more elaborate scenarios involving multiple black holes or connections between black holes and wormholes that might create traversable time machines. For instance, if two rotating black holes could be linked through a traversable wormhole, with one end experiencing significant time dilation relative to the other, it might theoretically create a usable time machine. However, maintaining such connections would require exotic matter with negative energy density, something we've never observed in sufficient quantities in nature. The theoretical physicist Kip Thorne and his colleagues explored this possibility in detail, calculating the exact properties that such a wormhole would need to function as a time machine. They determined that while nothing in Einstein's equations explicitly forbids such configurations, the energy requirements would be staggering, far beyond anything our civilization could generate with foreseeable technology. Moreover, the exotic matter needed would require energy states that violate what physicists call energy conditions, fundamental assumptions about how energy behaves in our universe. While quantum effects do allow for small temporary violations of these energy conditions through phenomena like the Casimir effect, scaling these up to maintain a macroscopic wormhole remains purely speculative. Equally fascinating is the idea of using a naturally occurring Einstein-Rosen bridge, the technical term for the simplest type of wormhole, connecting a black hole to a white hole, a theoretical time-reverse black hole from which matter can only exit but never enter. While classical general relativity suggests such bridges would collapse too quickly for anything to traverse them, some quantum gravity approaches suggest mechanisms by which they might be stabilized. If such stable bridges could exist, they might connect not just different regions of our universe, but different eras, effectively creating a bridge through time as well as space. These speculative scenarios highlight a profound limitation in our current understanding. The mathematics of general relativity breaks down at singularities. The theory predicts its own failure at these points, signaling the need for a more comprehensive framework incorporating quantum effects, a theory of quantum gravity. Such a theory might resolve the infinities at singularities and clarify whether closed time-like curves can actually exist or are merely mathematical artifacts of an incomplete theory. Several candidate approaches to quantum gravity, including string theory, loop quantum gravity, and asymptotic safety, suggest that singularities might be replaced by more complex structures where extreme but finite energy densities prevent spacetime from collapsing to a mathematical point. If true, this could dramatically change our understanding of black hole interiors and their relationship to time travel. In loop quantum gravity, for instance, the singularity might be replaced by a bounce that connects our universe to another expanding region, effectively a new universe born from the collapsed matter of a black hole. Other theories suggest connections to parallel universes or to distant regions of our own universe. These ideas remain highly speculative, but illustrate how the journey into a black hole connects directly to the frontiers of theoretical physics. The fate of information falling into black holes represents another profound puzzle that might illuminate the relationship between black holes and time. Quantum mechanics insists that information cannot be destroyed, yet black holes seem to erase the details of whatever falls into them. This black hole information paradox has driven theoretical work for decades. Stephen Hawking initially argued that information is indeed lost in black holes, requiring a modification of quantum mechanics. Later, developments in string theory suggested that information might be preserved in subtle quantum correlations in Hawking radiation, or stored at the event horizon in complex patterns. Some researchers propose that information might be simultaneously preserved and destroyed due to quantum complementarity, appearing different depending on the observer's perspective. This discussion of information preservation connects directly to time travel possibilities. If information about the past is truly erased by black holes, then perfect reconstruction of past states, essential for certain concepts of time travel, might be fundamentally impossible. Conversely, if information is preserved in some form, it raises questions about whether this stored information could theoretically be accessed or utilized. The most recent developments in this field involve concepts like the firewall paradox and ER-EPR conjecture, proposed by physicists including Juan Maldacena, Leonard Susskind, and others. These ideas suggest profound connections between quantum entanglement and space-time geometry that might resolve paradoxes about black hole interiors. Some of these approaches propose that falling into a black hole might connect to other regions of space-time through quantum entanglement, potentially offering new perspectives on time travel possibilities. Despite these theoretical explorations, the practical reality remains stark. Falling into a black hole would be fatal. No physical mechanism known to science would allow an object to survive the journey to the singularity, and certainly not to communicate back to the outside universe. Black holes represent one-way streets in the cosmos, regions where our understanding of physics approaches its limits and perhaps breaks down entirely. The fatal nature of black hole interiors stems not just from extreme gravity, but from the fundamental structure of space-time itself. As you approach the singularity, tidal forces grow without bound. Even for supermassive black holes, where you might cross the event horizon without immediate destruction, the singularity eventually awaits. These tidal forces would distort matter at the atomic and subatomic level, breaking molecular bonds and eventually disrupting the fundamental particles themselves. The human body, or indeed any physical structure, simply cannot maintain integrity under such conditions. Additionally, the extreme curvature of spacetime near singularities would distort the laws of physics as we understand them. The behavior of fields and forces would become unpredictable. Quantum effects would become increasingly important. Yet our current theories don't adequately describe quantum physics in such extremely curved spacetime. In essence, we would be entering a domain where the rulebook of physics as we know it no longer applies. Some speculative theories suggest that singularities might actually be averted by quantum effects. In approaches like loop quantum gravity, the energy density might reach a maximum value before bouncing back, preventing the formation of a mathematical singularity. If true, this could mean that falling into a black hole might lead not to a point of infinite density, but to something else. Possibilities include a transition to another universe, a white hole explosion in a different region of space-time, or other exotic scenarios that remain purely theoretical. Even if such alternatives to singularities exist, however, no known physics would allow the falling observer to survive the journey or return to their original space-time. Yet these thought experiments about journeying into black holes have profound value. They push our theories to their breaking points, revealing where new physics might be needed. They illuminate the deep connections between gravity, quantum mechanics, and the nature of space-time itself. And they highlight how black holes, while unlikely to serve as practical time machines, naturally create conditions where time flows at dramatically different rates. A form of time dilation that represents the closest thing to time travel we know to exist in nature. As we pull back from our imaginary plunge into a black hole, we're left with a profound appreciation for how these cosmic objects challenge our understanding of reality. While crossing the event horizon would be a one-way journey ending in destruction rather than time travel, the physics of black holes continues to illuminate possibilities for more exotic space-time structures that might theoretically allow for more dramatic forms of time manipulation. This brings us to wormholes, theoretical tunnels through space-time that might connect black holes to other regions of our universe, or even to other universes entirely. While distinct from black holes in important ways, wormholes share deep connections with them in both physics and popular imagination. Let's explore these hypothetical bridges through space-time and their potential relationship to time travel. Having explored the nature of black holes and their profound effects on space-time, we now turn our attention to perhaps an even more esoteric possibility: wormholes. These theoretical tunnels through the fabric of space-time could potentially connect distant regions of our universe, or even different universes entirely, creating shortcuts that might circumvent the normal limitations of space and time. But are wormholes merely mathematical curiosities? Or might they represent actual structures that could someday be utilized for interstellar travel or even time travel? Let's journey through the fascinating physics of these hypothetical cosmic passages. The concept of wormholes emerged from the same mathematical foundation that predicted black holes: Einstein's general theory of relativity. In 1935, just 2 decades after Einstein published his revolutionary theory, physicist Albert Einstein and his colleague Nathan Rosen discovered a solution to Einstein's field equations that described a bridge connecting 2 separate regions of space-time. This theoretical structure, initially called an Einstein-Rosen bridge, represented the first mathematical description of what we now call a wormhole. It's worth noting that Einstein and Rosen weren't searching for shortcuts through space when they discovered this solution. They were actually attempting to create a mathematical model of elementary particles using the framework of general relativity. Their discovery of the bridge connecting 2 regions of space-time was essentially a byproduct of this research. The term wormhole itself wasn't coined until much later, in 1957, by physicist John Wheeler, the same scientist who popularized the term black hole. Wheeler's vivid description compared these theoretical tunnels to the holes that worms create through apples, providing a shortcut from one surface to another. The original Einstein-Rosen bridge connected the interior of a black hole to a white hole, a theoretical time-reversed version of a black hole from which matter can only exit but never enter. This connection would theoretically create a tunnel through space-time, offering a potential shortcut between the 2 regions. However, Einstein and Rosen quickly realized that their bridge would collapse so rapidly that nothing, not even light, could traverse it. The bridge would pinch off before any signal or object could make it through, rendering it useless for actual travel. For decades, wormholes remained primarily a mathematical curiosity, rather than a serious subject for physical inquiry. This changed in 1988, when physicists Michael Morris, Kip Thorne, and Ove Yurtsever published a landmark paper exploring the possibility of traversable wormholes. Wormholes that could, at least theoretically, be traveled through by physical objects or signals. Their work reignited scientific interest in wormholes and their potential implications for both interstellar travel and time travel. To understand wormholes, we often use a 2-dimensional analogy. Imagine our universe as a flat sheet of paper. Normally, to travel from one point to another, we must move along the surface of the paper. But if we fold the paper so that distant points touch, we could create a shortcut by punching a hole through both layers. This simplistic model captures the essential concept. A wormhole creates a tunnel that bypasses the normal path through space, potentially allowing for shortcuts across vast cosmic distances. In reality, of course, our universe has 3 spatial dimensions plus time. A real wormhole would connect different regions of this 4-dimensional spacetime, creating a tunnel that could theoretically reduce travel times across astronomical distances. Instead of taking thousands or millions of years to reach distant galaxies, wormhole travelers might arrive in mere moments, assuming such structures could be found or created and stabilized for travel. This potential for faster-than-light travel in relation to external space, though not faster than light within the wormhole itself, makes wormholes a staple of science fiction, appearing in works like Star Trek, Stargate, Contact, and countless other stories. But the scientific reality of wormholes proves far more challenging than their fictional counterparts suggest. The primary obstacle to traversable wormholes lies in their stability. The same gravitational forces that make wormholes theoretically possible also tend to cause them to collapse almost instantaneously. When Morris, Thorne, and Yurtsever studied traversable wormholes, they discovered that keeping a wormhole open would require a form of matter or energy with negative mass or negative energy density, what physicists call exotic matter. Exotic matter would have the remarkable property of exerting repulsive gravity, pushing rather than pulling, which could theoretically counteract the natural tendency of a wormhole to collapse. The problem? We've never directly observed exotic matter with the properties and in the quantities needed to maintain a macroscopic wormhole. While quantum physics does permit small, temporary violations of energy conditions through phenomena like the Casimir effect, where quantum fluctuations between 2 closely spaced plates create a small region of negative energy density, scaling this effect up to stabilize a wormhole large enough for travel remains purely speculative. Despite this challenge, wormholes continue to fascinate physicists for several reasons. First, nothing in Einstein's equations explicitly forbids their existence. Second, they illuminate the rich structure of spacetime permitted by general relativity. And third, they connect to profound questions about causality and time travel, particularly when considering wormholes, where one mouth experiences more time dilation than the other. This brings us to perhaps the most intriguing aspect of wormholes, their potential relationship to time travel. If one mouth of a wormhole remains stationary while the other accelerates to relativistic speeds, or sits in a strong gravitational field, like near a black hole, time dilation would cause the 2 mouths to exist at different moments in time from an external perspective. Entering the slower time mouth and exiting from the faster time mouth could, theoretically, allow for travel backward in time relative to the external universe. Physicist Kip Thorne explored this possibility in detail, calculating the exact properties required for a wormhole to function as a time machine. He determined that if a wormhole could be created and maintained with sufficient exotic matter, and if one mouth were moved or placed in an appropriate gravitational field, it could indeed form what physicists call a closed time-like curve, a path through spacetime that returns to its starting point in time, as well as space. This theoretical possibility raises immediate concerns about causality paradoxes. The most famous is the grandfather paradox. If you traveled back in time and prevented your grandfather from meeting your grandmother, you would never be born. But if you were never born, how could you travel back in time to interfere with their meeting? Such circular reasoning creates logical loops that seem impossible to resolve. Thorne and others have proposed several possible resolutions to these paradoxes. One approach involves the consistent histories principle, which suggests that the laws of physics might somehow prevent inconsistent outcomes. You might try to change the past, but something would always happen to prevent paradoxical results. Your gun would jam, you would change your mind, or some other event would intervene to preserve consistency. Another approach involves the many worlds interpretation of quantum mechanics, which suggests that traveling back in time might create a new timeline or branch in reality, leaving the original timeline intact. In this view, you could change the past, but only in a newly created parallel universe, avoiding paradoxes in your original timeline. A third possibility, proposed by physicist Igor Novikov in the 1980s, is the self-consistency principle, which suggests that the laws of physics might only allow for consistent time loops. In this view, you could travel back in time, but would find yourself unable to change events in ways that would create paradoxes. The universe would somehow conspire to prevent inconsistent outcomes. You might try to shoot your grandfather, for instance, but the gun would jam, or you'd miss, or some other event would intervene to ensure that history remains consistent with your existence. These different approaches to resolving time travel paradoxes reflect a deeper question. Is the past fixed and unchangeable, or is it malleable? Our everyday experience suggests the past is immutable. Once events have occurred, they cannot be undone. But some interpretations of quantum mechanics raise intriguing questions about whether this fixity is fundamental or merely appears that way due to our macroscopic perspective. The debate about time travel paradoxes extends beyond physics into philosophy, raising profound questions about free will, determinism, and the nature of time itself. If the universe enforces self-consistency in time loops, does that mean travelers to the past lack free will? Or does it suggest a universe of multiple timelines where all possibilities exist simultaneously? These questions connect wormhole physics to some of humanity's oldest philosophical puzzles about the nature of time and causality. Regardless of how paradoxes might be resolved, the practical challenges of creating and maintaining traversable wormholes remain immense. The exotic matter requirements alone place wormhole travel far beyond our current technological capabilities. Some estimates suggest that creating a wormhole just 1 meter in diameter would require negative energy equivalent to converting the entire mass of Jupiter into pure energy, and then making that energy negative rather than positive. Even if these energy requirements could somehow be met, other practical issues arise. How would we create wormholes in the first place? How would we position their mouths where we want them? How would we prevent dangerous radiation from passing through the wormhole along with travelers? These engineering challenges, combined with the exotic matter requirement, place wormhole travel firmly in the realm of highly speculative future technology rather than near-term possibility. Despite these formidable obstacles, some theoretical physicists continue to explore whether wormholes might occur naturally in our universe. One possibility involves wormholes at the microscopic scale, quantum wormholes far too small for human travel, but potentially significant for understanding the fundamental structure of space-time. Physicist Juan Maldacena and others have explored how quantum entanglement, the mysterious connection between particles that Einstein called spooky action at a distance, might be related to tiny wormholes connecting entangled particles. This revolutionary idea emerged from studies of black hole thermodynamics and holography in string theory. In 2013, Maldacena and Leonard Susskind proposed what's now known as the ERA-EPR conjecture, suggesting that entangled quantum particles might be connected by microscopic wormholes. If true, every entangled particle pair in the universe could be linked by these tiny space-time tunnels. The implications are staggering. Quantum entanglement, which we can readily create in laboratories, might be a manifestation of microscopic space-time connections. The mathematics supporting this connection is complex but compelling. In certain theoretical frameworks, the equations describing quantum entanglement between particles bear striking similarities to equations describing connected space-time geometries. This has led some physicists to propose that space-time itself might not be fundamental but emergent, arising from more basic quantum relationships between entangled systems. In this view, the fabric of reality might be woven from threads of quantum entanglement, with wormholes representing the physical manifestation of these connections. Another speculative possibility involves primordial wormholes that might have formed during the extreme conditions of the early universe. In the first fraction of a second after the Big Bang, quantum fluctuations in spacetime might have created microscopic wormholes. Most would have collapsed immediately, but some theories suggest that inflation, the exponential expansion of the early universe, might have stretched some of these wormholes to macroscopic size, potentially leaving stable wormholes scattered throughout the cosmos. If such naturally occurring wormholes exist, they would likely be extremely rare and difficult to detect. How would astronomers even recognize a wormhole if they saw one? One approach might involve looking for unusual gravitational lensing effects, the bending of light around massive objects. A wormhole might produce distinctive patterns different from those created by normal stars or black holes. Alternatively, unusual motion of stars near an invisible gravitational source might indicate the presence of a wormhole rather than a conventional object. Surprisingly, some astronomers have already begun searching for evidence of wormholes in our galaxy. In 2019, a team of researchers proposed that the supermassive black hole at the center of our Milky Way, Sagittarius A star, might actually be the mouth of a wormhole. They suggested that careful observations of stars orbiting this central object might reveal subtle deviations from the orbits expected around a conventional black hole. While highly speculative, such research demonstrates how the theoretical possibility of wormholes is beginning to influence observational astronomy. Another detection approach involves gravitational waves. Ripples in spacetime, detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. Some theorists suggest that if a massive object passed through a wormhole, it might generate a distinctive gravitational wave signature different from those produced by black hole or neutron star mergers. Future gravitational wave observatories with increased sensitivity might be capable of detecting such signatures if they exist. Intriguingly, wormholes might also provide a potential explanation for certain cosmic mysteries. Some researchers have speculated that anomalies in cosmic ray observations or unexplained features in the cosmic microwave background radiation might be evidence of other universes connected to ours through wormholes. While these ideas remain highly speculative, they illustrate how wormhole physics intersects with questions about the largest structures and most fundamental aspects of our universe. The relationship between black holes and wormholes remains an area of active theoretical research. Some physicists have proposed that black holes might naturally form connections to other regions of spacetime through wormholes. In one speculative scenario, the information that falls into a black hole might escape through such connections, potentially resolving the infamous black hole information paradox, where quantum information seems to be destroyed, contradicting quantum mechanics. Recent work by physicists Stephen Hawking and others suggested that black holes might not actually have event horizons in the traditional sense, but rather apparent horizons that could eventually dissolve. In this view, what we perceive as a black hole might actually be a complex structure potentially involving wormhole-like connections, though these would still not be traversable in any practical sense. The mathematics of general relativity permits even more exotic possibilities involving multiple connected wormholes. Physicist Kip Thorne and his students explored Roman rings, arrangements of multiple wormholes connected in a ring configuration, which might allow for more stable time machine configurations than single wormholes. Similarly, multiple wormholes connecting different regions of spacetime could theoretically create networks or subway systems linking distant parts of the universe. These complex wormhole networks introduce additional theoretical possibilities for both space and time travel. For instance, a network of wormholes strategically placed throughout the galaxy could enable rapid transit between star systems without requiring any individual wormhole to span enormous distances. Such a network might develop naturally or could potentially be constructed by a sufficiently advanced civilization. Science fiction authors like Alastair Reynolds in his Revelation Space series have explored the idea of ancient wormhole networks left behind by precursor civilizations. providing a plausible mechanism for interstellar travel within the constraints of relativistic physics. From a time travel perspective, multiple connected wormholes introduce the possibility of more complex temporal loops and networks. Theoretical physicist Matt Visser has explored Roman configurations, specific arrangements of wormholes that might allow for controlled time travel while minimizing the risk of paradoxes. These configurations could theoretically create closed time-like curves that loop back on themselves in time, but with specific constraints that might prevent problematic causality violations. The mathematical descriptions of these complex wormhole arrangements highlight an important point about theoretical physics. Solutions to Einstein's equations can describe arrangements of matter and energy that, while mathematically consistent, might be physically impossible to create. The gap between mathematical possibility and physical realizability remains one of the key challenges in assessing whether wormholes could ever be harnessed for practical travel. However, a significant barrier to all these possibilities emerged from Stephen Hawking's work on chronology protection. Hawking proposed that the laws of physics might fundamentally prevent the creation of closed time-like curves, paths that would allow for backward time travel. According to his chronology protection conjecture, quantum effects near a would-be time machine would build up, creating a runaway energy accumulation that would destroy the wormhole before it could be used for time travel. Hawking expressed this principle memorably: "Nature abhors a time machine." While not definitively proven, this conjecture suggests that the universe might have built-in safeguards preventing causality violations through wormholes or any other mechanism. If true, wormholes might still be possible for interstellar travel, but would be prevented from functioning as time machines. Despite these theoretical challenges, wormholes continue to inspire both scientific research and public imagination. The possibility, however remote, of shortcuts through spacetime represents one of the few conceptual pathways to practical interstellar travel, given the vast distances separating star systems. Even reaching the nearest star system, Alpha Centauri, would take over 4 years traveling at light speed, and current spacecraft travel thousands of times slower than that. Wormholes offer at least a theoretical hope of overcoming these cosmic distances. In popular culture, wormholes often appear with visual effects that attempt to convey their strange nature: swirling tunnels, kaleidoscopic light patterns, or distorted spacetime. While visually dramatic, these depictions can't capture the mathematical reality of a four-dimensional tunnel through spacetime. The actual experience of traversing a wormhole, if it were ever possible, would likely be unlike anything we can properly visualize or simulate. The scientific exploration of wormholes represents a perfect example of how Einstein's theories continue to yield surprising possibilities a century after their formulation. When Einstein published his theory of general relativity in 1915, he could hardly have imagined the rich landscape of exotic objects it would eventually predict: black holes, gravitational waves, cosmic expansion, and wormholes among them. Many of these predictions seemed like mathematical curiosities for decades before astronomical observations confirmed their physical reality. Whether wormholes will join the list of confirmed predictions or remain theoretical possibilities depends on future advances in both theory and observation. The unification of quantum mechanics and general relativity, a still elusive theory of everything, might clarify whether wormholes can exist and under what conditions. Meanwhile, increasingly powerful astronomical instruments might someday detect evidence of naturally occurring wormholes, if they exist. For now, wormholes remain one of the most intriguing theoretical possibilities in modern physics, a window into the extreme flexibility of spacetime permitted by Einstein's equations. While practical wormhole travel or wormhole-based time machines remain firmly in the realm of science fiction rather than near-term technology, their study continues to illuminate the nature of space, time, and gravity. The mathematics that describes them connects to some of the deepest questions in theoretical physics: the information paradox, the emergence of space-time, the nature of quantum gravity, and the possibility of other universes beyond our own. The continued scientific interest in wormholes illustrates an important aspect of theoretical physics. Concepts that initially seem purely speculative can sometimes lead to profound scientific insights. When black holes were first proposed, they too seemed like mathematical curiosities rather than real objects. Decades later, we've not only confirmed their existence, but directly imaged them and detected the gravitational waves they produce when merging. While wormholes present even greater theoretical and practical challenges, their study continues to inspire new approaches to understanding the fundamental nature of reality. Perhaps most importantly, wormhole physics highlights the remarkable fact that our universe's underlying rules, as described by Einstein's equations, permit structures and phenomena far stranger than our everyday experience suggests. Whether or not traversable wormholes exist in nature or could ever be constructed, the mathematics describing them reveals a universe richer and more flexible than classical physics ever indicated. The fact that time travel isn't explicitly forbidden by our most successful theory of space-time continues to fascinate physicists and non-physicists alike, spurring both rigorous research and imaginative speculation. As our understanding of quantum gravity advances, and as astronomical observations become increasingly precise, we may someday determine whether wormholes exist naturally in our universe. Until then, they remain one of physics' most tantalizing possibilities, a reminder that reality may contain pathways and connections far more exotic than our limited experience suggests. As we journey back from these theoretical horizons to more established science, we should address another intriguing possibility related to both black holes and wormholes: closed time-like curves. These paths through space-time that return to their starting point in time represent perhaps the most direct theoretical route to backward time travel permitted by general relativity. Let's explore these strange loops in the fabric of space-time and their implications for the possibility of time travel. Imagine drawing a line on a piece of paper. The line moves forward, never crossing itself, always progressing in one direction. This is how we typically think of time, a straight arrow moving relentlessly from past to future. But what if that line could bend back on itself, creating a loop? This is the fascinating concept of a closed time-like curve, or CTC, one of the most intriguing theoretical constructs in modern physics, and potentially the key to understanding time travel through black holes. In the realm of Einstein's relativity, space-time isn't just a passive backdrop against which events unfold. It's a dynamic fabric that can stretch, bend, and perhaps even fold back upon itself. Closed time-like curves represent paths through space-time that, remarkably, return to their starting point not just in space, but in time. If you could travel along such a curve, you might find yourself arriving back where and when you started. This isn't science fiction. It's a mathematically valid solution to Einstein's field equations under certain conditions. The connection to black holes becomes clear when we consider the extreme warping of space-time near these cosmic giants. Near a rotating black hole, space-time doesn't just curve. It gets dragged along in a phenomenon physicists call frame dragging. This effect becomes particularly intense in what's known as the ergosphere, the region just outside a rotating black hole's event horizon. Some theoretical models suggest that in this chaotically twisted region of space-time, closed time-like curves might naturally form. I was initially skeptical about closed time-like curves, a theoretical physicist might tell you. But the mathematics kept pointing in their direction. The equations don't rule them out. In fact, they seem to invite their existence under extreme conditions. Picture yourself in a spacecraft with extraordinary capabilities, orbiting a supermassive rotating black hole. As you navigate through the intense gravitational field, following a precisely calculated path through the ergosphere, you might, according to these theoretical models, find yourself traveling along a route that eventually returns you to your starting point in both space and time. You could, in principle, meet your past self setting out on the journey, but creating or finding stable closed time-like curves presents monumental challenges. The energy requirements would be astronomical, potentially requiring what physicists call exotic matter. theoretical material with negative energy density that could counteract the natural tendency of wormholes to collapse and stabilize potential time loops. Such exotic matter hasn't been definitively observed in nature, though quantum fluctuations and the Casimir effect provide tantalizing hints of negative energy states that might make such materials possible. Another approach involves massive cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe. If two such strings were to pass by each other at nearly the speed of light, the resulting distortion in space-time might create conditions where closed time-like curves could form. Again, we're in the realm of fascinating theory rather than experimental reality. The Russian physicist Igor Novikov proposed a self-consistency principle to address the paradoxes that might arise from closed time-like curves. This principle suggests that only self-consistent trips through time would be physically possible. In other words, the universe somehow enforces consistency, preventing paradoxical situations from arising in the first place. Under this principle, you could travel back in time, but would find yourself unable to change events in ways that would create logical paradoxes. Think of it like trying to swim against the current of a river, an astrophysicist might explain. The laws of physics would subtly conspire to prevent you from creating inconsistencies, no matter how hard you tried to change the past. Some theoretical models suggest closed time-like curves might exist naturally at the quantum level, where the rigid rules of causality we experience in our macroscopic world might be more flexible. In quantum mechanics, cause and effect already have a more complex relationship than in classical physics. Particles can appear to influence each other instantaneously across vast distances through quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. The intersection of quantum mechanics with general relativity at the boundaries of black holes might reveal new possibilities for time-like curves that loop back on themselves. The quantum information paradox, the question of what happens to information that falls into a black hole, might be resolved through mechanisms that involve closed time-like curves at the quantum level. Rotating black holes, particularly those described by the Kerr metric in general relativity, present the most promising cosmic environments for the formation of closed time-like curves. Inside the inner event horizon of a Kerr black hole lies a region where conventional notions of space and time break down. Theoretical models suggest this inner region might contain closed time-like curves as a natural feature of its space-time geometry. The equations tell us something profound might be happening inside these rotating giants, a cosmologist might observe. The inner structure of Kerr black holes is one of the last great frontiers in classical general relativity. If closed time-like curves exist, they would fundamentally challenge our understanding of causality, the principle that cause must precede effect. They would force us to reconsider the nature of free will and determinism. Would the universe unfold according to a fixed script, with closed time-like curves simply revealing the inevitable? Or does quantum uncertainty provide wiggle room for multiple possible futures and pasts? Some physicists propose the chronology protection conjecture, formulated by Stephen Hawking, which suggests that the laws of physics ultimately forbid the creation of closed time-like curves. According to this conjecture, whenever conditions approach those that might form a closed time-like curve, quantum effects would generate massive energy fluctuations that would prevent the curve from forming. The universe, in this view, protects itself from the logical paradoxes that time travel might introduce. Nature, Hawking once remarked, abhors a time machine. Yet the mathematics keeps pointing to these fascinating loops in time. In 2009, physicists demonstrated that closed time-like curves are fully compatible with quantum mechanics, suggesting the possibility of solving otherwise unsolvable problems through time travel computing that utilizes these temporal loops. While practical implementation remains far beyond our current technological capabilities, the theoretical foundation continues to intrigue researchers. For a moment, let's indulge in a thought experiment. Imagine a civilization with technology millions of years more advanced than our own, capable of harnessing the energy of entire stars. Could they potentially create stable, closed, time-like curves using carefully engineered black holes? Could they build a network of these temporal loops, creating what we might think of as a subway system through time itself? The energy requirements would be staggering, perhaps requiring the output of multiple stars. But the laws of physics, as we currently understand them, don't entirely rule out such a possibility. The engineering challenges would be immense, involving the precise manipulation of space-time itself, but again, not theoretically impossible given sufficiently advanced technology. Another fascinating aspect of closed time-like curves is how they might interact with the concept of entropy and the second law of thermodynamics. This fundamental law tells us that entropy, roughly speaking, the measure of disorder in a system, always increases over time. It's why eggs break but don't unbreak, why heat flows from hot objects to cold ones but not the reverse. This irreversible arrow of time seems baked into the fabric of our universe, but closed time-like curves potentially challenge this one-way progression. If you could travel along a closed time-like curve, revisiting earlier moments in time, what would happen to entropy? Would you witness processes running backward, like watching a movie in reverse? Or would entropy continue to increase even along a loop in time, creating a kind of spiral rather than a perfect circle? These questions remain unresolved and represent one of the most profound challenges closed time-like curves pose to our understanding of physics. The mathematical foundation for closed time-like curves dates back to 1949, when Kurt Gödel, already famous for his incompleteness theorems in mathematics, discovered a solution to Einstein's field equations that allowed for closed time-like curves. Gödel's universe was rotating, and this rotation created conditions where time-like paths could loop back on themselves. Einstein himself was troubled by this implication of his own theory, as it suggested the possibility of time travel, which he found philosophically disturbing. Since Gödel's discovery, physicists have found numerous other solutions to Einstein's equations that permit closed time-like curves. The Tipler cylinder proposed by Frank Tipler in 1974 consists of an infinitely long, ultra-dense cylinder, rotating at speeds approaching that of light. The intense frame-dragging effect near such a cylinder could, theoretically, create closed time-like curves. While an infinite cylinder isn't physically realistic, a sufficiently long and dense one might produce similar effects in a limited region. The challenges of observing or testing for closed time-like curves are enormous. Unlike other predictions of general relativity, such as gravitational waves, which were detected in 2015, a century after Einstein predicted them, closed time-like curves remain in the realm of theoretical possibility. The extreme conditions where they might form, near rotating black holes or other exotic cosmic structures, lie far beyond our current observational capabilities. Some physicists have proposed experimental tests for closed time-like curves in quantum systems. In 2014, researchers suggested a framework for testing the existence of quantum-closed, time-like curves in the laboratory using quantum entanglement. While these experiments wouldn't create actual time loops, they might reveal whether quantum mechanics allows for the kind of information flow that closed time-like curves would permit. The philosophical implications of closed time-like curves extend far beyond physics into metaphysics and the philosophy of time itself. If closed time-like curves exist, does that mean the future is already fixed, already out there, waiting to be discovered? Or does it suggest a more complex relationship between past, present, and future? Perhaps a multiverse where different timelines branch off from each choice point. These questions touch on ancient philosophical debates about fate, free will, and the nature of time. The Greek philosopher Parmenides argued that change is an illusion, that everything that will happen already exists timelessly. In contrast, Heraclitus famously claimed that you cannot step into the same river twice, emphasizing the constant flux of reality. Closed time-like curves seem to suggest a universe that is somehow both a block universe where everything exists timelessly, yet one where cause and effect still have meaning within the loop. When I contemplate closed time-like curves, a philosopher of physics might tell you, I'm struck by how they challenge our most basic intuitions about time. They force us to question whether our experience of time as flowing in one direction is fundamental to reality or merely an artifact of our limited perspective. For science fiction writers, closed time-like curves have provided rich material for storytelling. From H.G. Wells' The Time Machine to modern films like Interstellar, the possibility of traveling through time has captivated our imagination. What's remarkable is that these seemingly fantastical stories might contain a kernel of physical possibility grounded in the mathematics of Einstein's relativity. The ethical questions raised by potential time travel are equally profound. If closed time-like curves were somehow harnessed for practical time travel, what responsibilities would time travelers bear? Would there be a moral obligation not to interfere with past events? Or would the very existence of closed time-like curves imply that such interference is part of the consistent fabric of space-time? Some physicists have proposed that closed time-like curves, if they exist, might be subject to cosmic censorship, the same theoretical principle that might hide singularities from external observers. The universe might allow these loops in time to exist mathematically, but place them behind event horizons or other barriers that prevent their use for practical time travel. The search for closed time-like curves continues to drive theoretical research at the intersection of general relativity and quantum mechanics. As we develop more sophisticated mathematical models and observational techniques, we edge closer to understanding whether these fascinating loops in time could really exist in our universe. The journey involves not just physics, but philosophy, challenging us to reconsider our most fundamental assumptions about the nature of time itself. Let's consider how closed time-like curves might manifest in specific cosmic environments. Supermassive black holes at the centers of galaxies, like the one at the heart of our own Milky Way known as Sagittarius A star, represent potential laboratories for these extreme space-time conditions. With masses millions or billions of times that of our Sun, these cosmic behemoths create gravitational fields of extraordinary intensity. If these black holes rotate, and astronomical observations suggest many do, they might create the specific conditions that theoretical models suggest could support closed time-like curves. Imagine a future space mission specifically designed to probe the ergosphere of a rotating black hole. Using advanced propulsion systems and shielding technologies beyond our current capabilities, such a mission might be able to detect signatures of closed time-like curves, perhaps subtle violations of conventional causality or unexpected quantum effects that suggest information traveling along loops in time. While such a mission remains far beyond our current technological horizon, it represents the kind of empirical approach that might one day provide evidence for or against the existence of these theoretical constructs. Some theorists have suggested that microscopic black holes, which might have formed in the extreme conditions of the early universe, could provide another environment where closed time-like curves might exist. These primordial black holes, if they rotate rapidly enough, might create miniature versions of the space-time conditions thought to support closed time-like curves. While detecting such primordial black holes presents enormous challenges, they represent another potential avenue for exploring these fascinating theoretical possibilities. The mathematics of closed time-like curves continues to evolve as physicists develop more sophisticated approaches to general relativity and quantum field theory. Recent work has explored how quantum effects might modify the classical picture of closed time-like curves, potentially resolving some of the paradoxes they seem to introduce. These approaches suggest that quantum mechanics might smooth out the sharp violations of causality that closed time-like curves seem to imply in classical physics, providing a more nuanced picture of how information might flow in loops through time. As we contemplate the possibility of closed time-like curves and their implications for time travel through black holes, we're faced with a series of paradoxes that seem to defy logic itself. What happens if you travel back in time and prevent your own birth? Can effects precede their causes? Can information be created from nothing, circling endlessly through a loop in time. These paradoxes aren't merely philosophical curiosities. They represent profound challenges to our understanding of the fundamental laws that govern our universe. They form the next chapter in our exploration of time travel through black holes, a journey that takes us to the very limits of our understanding of physical reality, where intuition falters and mathematics provides our only reliable guide. Picture this: you build a time machine, travel back 50 years, and accidentally prevent your grandparents from meeting. If they never meet, they never have your parent. If your parent is never born, you are never born. But if you're never born, how did you travel back in time to prevent your grandparents from meeting in the first place? This mind-bending scenario is the famous grandfather paradox, and it's just one of many logical conundrums that haunt the possibility of time travel. Time travel paradoxes have fascinated philosophers, physicists, and science fiction writers for generations. They represent the logical knots we tie ourselves in when we imagine traveling backward through time. And if black holes might somehow provide pathways through time, as we've been exploring, then we need to confront these paradoxes head-on. The grandfather paradox is perhaps the most well-known time travel paradox, but it's just one example of a broader class known as consistency paradoxes. These paradoxes arise when a time traveler's actions in the past create changes that would prevent the time travel from occurring in the first place. The resulting logical contradiction seems to suggest that time travel must be impossible, but physicists and philosophers have proposed several potential resolutions to these mind-bending paradoxes. One approach comes from quantum mechanics and is known as the many-worlds interpretation, originally proposed by physicist Hugh Everett in the 1950s. This interpretation suggests that every quantum event creates a branching of reality into multiple parallel universes. In the context of time travel, the many-worlds interpretation offers a fascinating solution. When you travel back in time and change something, you're not changing your own past, but creating a new timeline, a new branch of reality. In this new branch, your grandparents never meet, and you're never born, but you yourself are from the original branch where they did meet, explaining how you could exist to travel back in time in the first place. Think of time not as a single line, a theoretical physicist might explain, but as a tree with countless branches. When you travel back, you're not moving up and down the same line, but jumping to a different branch altogether. This interpretation eliminates the logical contradictions of the grandfather paradox, but introduces a new question. If time travelers create new timelines rather than changing their own, can we really call it time travel at all? Or is it more accurately described as timeline travel or parallel universe creation? Another resolution comes from the Novikov self-consistency principle, which we touched on earlier. This principle, proposed by Russian physicist Igor Novikov in the 1980s, suggests that the laws of physics somehow prevent inconsistent time loops from forming. According to this view, you could travel back in time, but you would find it impossible to change events in ways that would create paradoxes. Imagine trying to shoot your grandfather before he meets your grandmother. Under the Novikov principle, something would always prevent you from succeeding. The gun might jam, you might miss, or you might even have a change of heart at the last moment. The universe, in this view, conspires to maintain consistency. It's like trying to create a square circle, a philosopher of physics might say. The laws of logic simply don't allow it. Similarly, the laws of physics might not allow paradoxical situations to arise, even if time travel itself is possible. This self-consistency approach preserves the possibility of time travel while eliminating the logical contradictions of paradoxes. But it raises profound questions about free will. If you travel back in time, are your actions somehow constrained by the need to maintain consistency? Does this mean the future is already fixed, already determined? Perhaps the most perplexing time travel paradox is the bootstrap paradox, also known as the ontological paradox or causal loop. In this scenario, information or objects exist without ever having been created. They exist in a loop through time, with no discernible beginning or end. Imagine finding a book of advanced physics theories. Inspired by its contents, you spend decades building a time machine. Once completed, you travel back in time and give the book to your younger self, the very same book that inspired you to build the time machine in the first place. Where did the information in the book originally come from? It seems to exist in a loop, with no point of creation. The bootstrap paradox challenges our understanding of causality itself, the principle that effects must have causes. In a causal loop, effects become their own causes in a circular chain of events. Rather than A causing B and B causing C, we have A causing B, B causing C, and C causing A. The entire loop exists as a self-sustaining entity. The bootstrap paradox isn't necessarily a logical contradiction in the same way as the grandfather paradox, a philosopher might observe. It's strange and counterintuitive, but it doesn't involve the same kind of logical impossibility. It just forces us to abandon our usual notions of linear causality. Some physicists suggest that information in a bootstrap paradox might degrade over time, following the second law of thermodynamics. Imagine copying that physics book before sending it back in time. Each copy would contain tiny errors that would accumulate over many iterations of the loop, gradually changing the information. This entropy-based approach might provide a way to understand causal loops without abandoning causality entirely. The predestination paradox represents another fascinating twist in the logic of time travel. In this scenario, a time traveler's attempt to prevent an event actually causes that very event to occur. You travel back in time to prevent a fire, but in your attempt to do so, you accidentally knock over a lantern that starts the fire you were trying to prevent. This paradox suggests a universe where events are predetermined, where attempts to change the past are already woven into the fabric of history. The Greek myth of Oedipus reflects this ancient intuition. Oedipus's father learns from an oracle that his son will kill him and marry his wife. His attempts to prevent this prophecy by abandoning his infant son ultimately lead to its fulfillment, as Oedipus unknowingly kills his father and marries his mother years later. The predestination paradox doesn't involve the same logical contradictions as the grandfather paradox. It's perfectly consistent, just deeply unsettling in its implications for free will and the nature of time. It suggests a block universe where past, present, and future exist simultaneously, with all events already fixed. The information paradox adds another layer of complexity to time travel scenarios. If you could travel to the past and bring knowledge from the future, say tomorrow's stock prices or lottery numbers, you could create unlimited wealth with no apparent effort. This would seemingly violate fundamental principles of conservation that underlie our physical laws. Information has real value in our universe, an economist with an interest in physics might explain. Getting something for nothing, whether it's energy or information, tends to violate fundamental conservation principles. Time travel that allows free transport of information across time might be problematic for similar reasons. This leads to a broader question. If time travel through black holes were possible, would it allow for the violation of physical laws like conservation of energy or the second law of thermodynamics? Or would the mechanics of time travel somehow preserve these fundamental principles even while bending our notion of linear time? The twin paradox, while not strictly a time travel paradox in the same sense as the others, highlights the relative nature of time in Einstein's physics. One twin stays on Earth, while the other travels in a spaceship at nearly the speed of light. When the traveling twin returns, they've aged less than their Earthbound sibling due to time dilation. This isn't actually a logical paradox, but a counterintuitive consequence of special relativity. It demonstrates how time isn't absolute, but relative to the observer's frame of reference. Near black holes, where gravitational time dilation becomes extreme, these effects would be even more pronounced. The black hole information paradox, which we touched on earlier, represents another fascinating intersection between black holes and time. When matter falls into a black hole, quantum information seems to be lost, violating a fundamental principle of quantum mechanics that information cannot be destroyed. But if information somehow escapes from a black hole, perhaps through Hawking radiation or some other mechanism, it might effectively be traveling backward in time relative to an outside observer due to the extreme time dilation near the event horizon. The boundary of a black hole may be where our conventional understanding of time breaks down completely, a theoretical physicist might suggest. It's where general relativity meets quantum mechanics, and neither theory alone can fully describe what happens there. Some physicists have proposed that cosmic censorship, a theoretical principle suggested by Roger Penrose, might prevent time travel paradoxes from arising. According to this principle, singularities, like those at the centers of black holes, are always hidden behind event horizons, preventing the extreme physics of singularities from affecting the external universe. Similar principles might prevent closed time-like curves from being used for the kind of time travel that would create paradoxes. Recent theoretical work has explored how quantum mechanics might resolve time travel paradoxes. In the quantum realm, particles exist in probabilistic states rather than definite positions and velocities. This inherent uncertainty might provide wiggle room that allows for consistent time loops without strict determinism. In a fascinating series of thought experiments, physicists have shown that quantum particles sent along closed time-like curves could interact with their past selves in ways that avoid logical contradictions. These quantum time loops would follow different rules than the classical time travel scenarios that lead to paradoxes like the grandfather paradox. Quantum mechanics already challenges our intuitions about causality, a quantum physicist might point out. Quantum entanglement allows for correlations between particles that seem to violate our normal understanding of cause and effect. Perhaps quantum mechanics naturally accommodates the strange looping causality that time travel would introduce. If we consider the many worlds interpretation and quantum mechanics together, we arrive at an even more intricate picture of potential time travel. Perhaps time travelers don't create new timelines, but rather shift their consciousness between already existing parallel universes, selecting a path through the vast multiverse rather than changing any single universe's history. This approach, sometimes called the no-change view of time travel, suggests that time travelers could visit the past but would be unable to change the events they remember. Any apparent changes would actually represent shifts between parallel timelines that already existed. This preserves consistency while allowing for the subjective experience of time travel. Some theorists have proposed that black holes might connect not just to other regions of our universe through wormholes, but to other universes entirely in a vast multiverse. If this were the case, time travel through black holes might actually represent travel between different universes with different histories, providing another potential resolution to time travel paradoxes. The philosophical implications of these various approaches to time travel paradoxes are profound. They touch on fundamental questions about the nature of time, causality, free will, and determination. Is time fundamentally different from space, flowing in one direction only? Or is it more like another dimension of space, where movement in either direction is theoretically possible under the right conditions? The practical implications for potential time travelers would be equally profound. If the many worlds interpretation is correct, time travelers might need to accept that they could never return to their original timeline. Each journey would be one way, creating new branches of reality rather than altering existing ones. If the Novikov self-consistency principle holds, time travelers would face a universe that mysteriously prevents them from making paradoxical changes. They might find themselves acting out predestined roles in history, their apparent free will an illusion when it comes to events that might create inconsistencies. Among physicists and philosophers, the debate about time travel paradoxes continues. Some argue that the logical contradictions inherent in paradoxes, like the grandfather paradox, provide strong evidence that time travel to the past must be physically impossible, despite the mathematical solutions to Einstein's equations that seem to permit it. Others suggest that our discomfort with time travel paradoxes reflects the limitations of our evolved intuitions rather than actual logical impossibilities. After all, quantum mechanics and relativity have already forced us to abandon many intuitive notions about the nature of reality. Perhaps time travel paradoxes simply represent another area where our intuitions lead us astray. Throughout the history of physics, a historian of science might observe, we've repeatedly discovered that the universe is stranger than we imagined. From quantum mechanics to black holes, reality has surprised us again and again. Time travel paradoxes may represent another frontier where our intuitions need to catch up with the mathematics. As our understanding of physics continues to evolve, with ongoing efforts to reconcile general relativity and quantum mechanics in a theory of quantum gravity, we may gain new insights into the possibility of time travel and the nature of time itself. The extreme physics of black holes, where space-time is stretched and twisted to its limits, provides a natural laboratory for exploring these profound questions. Whether black holes could ever serve as time machines in any practical sense remains highly speculative, but the theoretical exploration of time travel paradoxes provides a valuable tool for probing the logical structure of our physical theories and the nature of time itself. Science fiction writers have explored time travel paradoxes with remarkable creativity, often anticipating concepts that physicists would later formalize. In Ray Bradbury's A Sound of Thunder, a time traveler accidentally steps on a butterfly in the prehistoric past, causing cascading changes that transform his present world when he returns. This story, published in 1952, popularized what's now known as the butterfly effect, the notion that tiny changes in initial conditions can lead to massive differences in outcomes over time. This concept connects to chaos theory in physics, where complex systems show extreme sensitivity to initial conditions. If time travel were possible, chaos theory suggests that even the smallest actions in the past might have unpredictable, potentially enormous consequences for the future. This raises a troubling question. Would any form of time travel inevitably alter the timeline in ways impossible to predict or control? The mathematics of chaos theory tells us something profound about time travel, a mathematician might explain. Even if we could somehow avoid direct paradoxes, the butterfly effect might make any visit to the past inherently transformative for the future. The mere displacement of air molecules as you move through the past could theoretically trigger atmospheric changes that, amplified over time, alter weather patterns worldwide. Some philosophers have proposed that certain events might be more resistant to change than others, what we might call historical inertia. Major historical events with multiple causes and widespread effects might naturally tend to occur despite a time traveler's interventions, while minor events with limited significance might be more easily altered. This concept appears in various forms in science fiction, where time travelers find they can change small details, but not the broad strokes of history. The field of quantum computation offers another fascinating perspective on time travel paradoxes. Theoretical work suggests that quantum computers with access to closed time-like curves could solve problems that are intractable even for ordinary quantum computers. This computational advantage comes from the ability to send information back in time within the computation, effectively creating shortcuts through the usual step-by-step processing. These theoretical models don't require sending physical objects or people back in time, just quantum information. They suggest that the apparent paradoxes of time travel might be resolved by the probabilistic, non-deterministic nature of quantum mechanics itself. In the quantum realm, particles exist in superpositions of states until measured, potentially allowing for consistent causal loops without the logical contradictions we encounter in classical physics. The renowned physicist John Wheeler proposed a fascinating thought experiment called delayed choice that illustrates the strange relationship between observation and reality in quantum mechanics. In these experiments, the choice of how to observe light seems to retroactively determine whether it behaved as a wave or a particle in the past. While not time travel in the conventional sense, these experiments suggest that quantum mechanics might already incorporate a form of backward causation, effects influencing their causes. that challenges our conventional understanding of time. What Wheeler's delayed choice experiments tell us, a quantum physicist might explain, is that our intuitive notions of before and after might not apply straightforwardly at the quantum level. Reality seems to be woven together in ways that transcend our ordinary understanding of causality. Beyond physics, time travel paradoxes raise profound questions about human psychology and agency. If we could visit the past, would we be psychologically capable of not attempting to change it, especially if confronted with historical tragedies? The ethical dimensions of time travel would be enormously complex. Would time travelers have a moral obligation to prevent past atrocities if they could? Or would the potential for creating paradoxes and unpredictable consequences make such interventions ethically problematic? Cultural attitudes toward time travel paradoxes vary significantly across societies. Western philosophical traditions tend to emphasize linear causality and logical consistency, making time travel paradoxes particularly troubling. Some Eastern philosophical traditions, by contrast, have long embraced cyclical conceptions of time and non-linear causality, potentially providing frameworks for understanding time travel that don't generate the same paradoxes. In Buddhist philosophy, a comparative philosopher might note, time isn't viewed as an absolute reality, but as part of the conventional reality we experience. The ultimate nature of reality transcends our ordinary concepts of time, causality, and identity. From this perspective, the paradoxes of time travel might reflect the limitations of conventional thinking rather than true logical impossibilities. If we consider black holes as potential gateways for time travel, we must also consider how the extreme physics at their boundaries might transform our understanding of paradoxes. Near the event horizon of a black hole, time and space exchange roles in a sense. Time becomes spatial-like, and one of the spatial dimensions becomes time-like. In this twisted region of space-time, our conventional notions of causality might break down entirely, requiring new frameworks for understanding what constitutes a paradox. The philosopher Karl Popper proposed the principle of falsifiability as a criterion for distinguishing scientific theories from non-scientific ones. A theory is falsifiable if it makes predictions that could potentially be proven wrong by observation or experiment. Time travel paradoxes raise an interesting question in this context. Is the possibility of time travel a falsifiable scientific hypothesis, or does it belong more to the realm of metaphysical speculation? While we can't currently test for time travel directly, the theoretical frameworks that suggest its possibility, particularly Einstein's general relativity, have been repeatedly tested and validated in other contexts. If these frameworks permit time travel under certain conditions, even if those conditions are extremes, then time travel remains within the realm of scientific inquiry rather than pure speculation. As we contemplate the paradoxes of time travel through black holes, we're forced to confront the limits of our understanding, not just of physics, but of logic, causality, and the nature of time itself. These paradoxes may represent genuine obstacles to time travel, or they may simply highlight the inadequacy of our current conceptual frameworks when dealing with the extreme conditions near black holes and other exotic space-time structures. Either way, the exploration of these paradoxes pushes us toward a deeper understanding of the universe and our place within it. Whether or not time travel through black holes ever proves practically possible, the theoretical investigation of its paradoxes enriches our understanding of the cosmos and challenges us to think beyond our intuitive notions of how reality works. As we move forward in our exploration of time travel through black holes, let's turn our attention to the real-world observations and experiments that might shed light on these theoretical possibilities. While we can't yet send probes through the event horizons of black holes to test for closed time-like curves directly, astronomers and physicists have developed ingenious methods for studying these cosmic behemoths from afar. What have we learnt so far, and what might future observations reveal about the true nature of black holes and their relationship to time? While time travel through black holes remains theoretical, our understanding of these cosmic phenomena has advanced dramatically in recent years. we've moved from mathematical abstractions to direct observations, capturing the first ever image of a black hole's shadow and detecting the gravitational waves from black hole mergers. These groundbreaking achievements mark the beginning of a new era in black hole research, one that might eventually shed light on the possibility of using these cosmic objects as gateways through time. The Event Horizon Telescope, a planet-scale array of radio telescopes, made history in April 2019 when it unveiled the first direct image of a black hole. This wasn't just any black hole, but the supermassive giant at the center of Galaxy M18. M87, located 55 million light-years from Earth. The image, showing a glowing ring of superheated gas surrounding a dark central shadow, confirmed predictions made by Einstein's theory of general relativity more than a century earlier. What's remarkable about this image, an astrophysicist might tell you, isn't just that we can see a black hole. By definition, the black hole itself emits no light and cannot be directly seen. What we're seeing is the shadow it casts against the bright background of glowing gas, along with the photon ring, light that orbits the black hole multiple times before reaching our telescopes. This photon ring represents light traveling in nearly circular paths around the black hole due to its extreme gravitational bending of spacetime. These photons orbit the black hole several times before either escaping to reach our telescopes or falling into the event horizon. This direct observation of light bending around a black hole provides compelling evidence for one of the key predictions of general relativity, the theory that also suggests the possibility of closed time-like curves under extreme conditions. The Event Horizon Telescope has since captured an image of Sagittarius, a star, the supermassive black hole at the center of our own Milky Way galaxy. At 4 million times the mass of our Sun, Sagittarius A star is much smaller than the AM87 black hole, but also much closer to Earth at just 26,000 light-years away. Imaging this black hole was like trying to spot a donut on the surface of the Moon, requiring extraordinary precision and coordination among observatories worldwide. These direct observations allow scientists to test Einstein's theory of general relativity in the strongest gravitational environments known to exist. So far, the theory has passed every test with flying colors. Since this same theory provides the mathematical foundation for closed time-like curves and potential time travel, each confirmation of general relativity keeps the theoretical door to time travel slightly ajar. Another revolutionary advancement came in September 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves for the first time. These ripples in space-time, predicted by Einstein a century earlier, were produced by the violent merger of two black holes approximately 1.3 billion light-years away. Gravitational waves are like the sound of space-time itself, a LIGO scientist might explain. When massive objects like black holes spiral together and merge, they create ripples that propagate through the universe at the speed of light. These ripples are incredibly subtle by the time they reach Earth, changing the length of our 4-kilometer detector by less than the width of a proton, but we can detect them with incredibly precise laser measurements. Since that first detection, LIGO and its European counterpart Virgo have observed dozens of gravitational wave events, most from black hole mergers. These observations provide unprecedented insights into the properties of black holes, including their masses, spins, and distributions throughout the universe. The spin of a black hole is particularly relevant to our discussion of time travel, as it's rotating black holes that theoretically allow for closed time-like curves. The gravitational wave detections confirm that black holes do indeed spin, sometimes at rates approaching the theoretical maximum. The black holes involved in the first detection were spinning at more than 100 million rotations per minute, an almost incomprehensible rate. These observations give us confidence that the mathematical models used to describe rotating black holes, particularly the Kerr metric in general relativity, accurately represent reality, since it's precisely these rotating black hole solutions that potentially allow for closed time-like curves. The confirmation of rapidly spinning black holes keeps the theoretical possibility of time travel alive. X-ray observatories like NASA's Chandra and NuSTAR, have provided another window into the environments around black holes. By studying the X-ray emissions from superheated gas spiraling into black holes, scientists can map the extreme distortions of space-time in these regions and even measure the spins of the black holes themselves. These observations reveal the effects of frame dragging, the way a rotating black hole pulls space-time around with it as it spins. This is the same effect that, taken to extremes near the event horizon, could theoretically lead to closed time-like curves. While we haven't observed closed time-like curves directly, we have confirmed the frame-dragging effect that forms a key part of the theoretical foundation for their existence. One particularly intriguing observation comes from studies of quasi-periodic oscillations in the X-ray emissions from matter falling into black holes. These oscillations occur at specific frequencies related to the orbital and epicyclic frequencies of matter in the extreme gravitational field near the event horizon. By analyzing these oscillations, scientists can test predictions of general relativity in regimes where gravity is far stronger than anywhere else we can observe. These quasi-periodic oscillations are like the black hole's heartbeat, an X-ray astronomer might tell you. They reveal the dynamics of space-time in regions where it's being stretched and twisted to the limits predicted by our theories. So far, the observations match our models remarkably well, giving us confidence that we understand the basic physics of these extreme environments. While these observations don't directly confirm or refute the possibility of time travel through black holes, they do validate the theoretical framework that suggests such possibilities in the first place. Each confirmation of general relativity in extreme gravitational environments provides another piece of evidence that this theory, with all its exotic implications, accurately describes the universe we inhabit. Laboratory experiments on Earth can't recreate the extreme conditions near black holes, but they can test related aspects of general relativity and quantum mechanics that bear on the question of time travel. Atomic clocks, for instance, are now so precise that they can detect the slowing of time due to changes in elevation of just a few centimeters on Earth's surface. If I raise one atomic clock just 1 foot higher than another, a precision measurement physicist might explain, I can measure the fact that time passes slightly faster for the higher clock because it's slightly farther from Earth's mass. This is exactly the effect that becomes so extreme near black holes that it might theoretically allow for closed time-like curves. These precision measurements of gravitational time dilation on Earth provide further confirmation of the relativistic effects that, taken to extremes near black holes, open the theoretical door to time travel. They demonstrate that time itself is malleable, flowing at different rates depending on gravitational potential and relative velocity, exactly as Einstein's theories predict. Quantum optics experiments have begun to probe some of the stranger aspects of time in quantum systems. The delayed choice quantum eraser experiment, for instance, seems to allow the observer's future choice to affect the past behavior of particles. While not true time travel in the macroscopic sense, these experiments suggest that at the quantum level, time might not flow strictly from past to future. What's fascinating about these quantum experiments, a quantum physicist might tell you, is that they challenge our intuitive notions of causality and the arrow of time. They suggest that at the most fundamental levels of reality, time might not work exactly as we experience it in our everyday lives. These quantum effects become particularly relevant when considering black holes, as the extreme conditions near the singularity would necessarily involve quantum gravity, the still developing theory that attempts to reconcile general relativity with quantum mechanics. While we don't yet have a complete theory of quantum gravity, these laboratory experiments provide tantalizing hints about how quantum effects might influence time itself. Future missions promise even more detailed observations of black holes and their effects on spacetime. The proposed Laser Interferometer Space Antenna, or LISA, would detect gravitational waves from supermassive black hole mergers across the universe. With its million-kilometer arms, LISA would be sensitive to gravitational waves at frequencies impossible to detect from Earth. The next generation of X-ray observatories, like the European Space Agency's Athena and NASA's proposed Lynx, will provide unprecedented resolution of the hot gas swirling around black holes. These observations will map the distortion of spacetime in these extreme environments with even greater precision, potentially revealing subtle effects relevant to understanding closed time-like curves. Advanced radio telescope arrays will build on the success of the Event Horizon Telescope, providing sharper images of black holes and potentially detecting signs of frame dragging and other effects directly. These observations might even reveal the detailed structure of the photon sphere, the region where light orbits a black hole multiple times, which plays a crucial role in some theoretical time travel scenarios. The next decade of black hole observations will be revolutionary, an astronomer might predict. We're moving from just detecting these objects to doing detailed studies of how they warp spacetime around them. Each new observation brings us closer to understanding whether phenomena like closed, time-like curves could really exist. Laboratory experiments with quantum entanglement continue to probe the fundamental nature of time and causality. Recent experiments have demonstrated quantum entanglement across significant distances and time intervals, suggesting that quantum correlations might transcend our conventional understanding of temporal ordering. These experiments relate to theoretical proposals for quantum time travel that avoid the classical paradoxes we discussed earlier. In the quantum realm, particles exist in superpositions of states with inherent uncertainty, potentially providing wiggle room for consistent, closed time-like curves without deterministic paradoxes. Computer simulations provide another approach to studying black holes and their effects on spacetime. Using supercomputers, scientists can model rotating black holes and the behavior of matter and light in their vicinity. These simulations can explore regimes that are difficult or impossible to observe directly, including the interior regions of black holes beyond the event horizon. With modern supercomputers, a computational physicist might explain, we can solve Einstein's equations numerically in situations where analytical solutions are impossible. This allows us to explore exotic scenarios involving extreme black holes, potentially including those that might allow for closed time-like curves. While these simulations can't tell us definitively whether time travel through black holes is possible, they can identify promising configurations and scenarios for further theoretical investigation. They can also predict observable signatures that astronomers might look for when studying real black holes. A particularly intriguing line of research involves searching for evidence of advanced civilizations that might have harnessed black holes for energy or even time travel. While highly speculative, astronomers have proposed methods for detecting the telltale signatures of black holes that have been engineered or modified by technological means. Such signatures might include unusual radiation patterns, unexpected orbital dynamics of nearby stars, or gravitational lensing effects that don't match theoretical predictions for natural black holes. While no such evidence has been found, the search itself represents an acknowledgement that the extreme physics of black holes might someday be harnessed for purposes we can barely imagine. The connection between black holes and information theory represents another promising avenue for understanding their relationship to time. In quantum information theory, the entropy of a black hole is proportional to its surface area rather than its volume, a surprising finding with profound implications for our understanding of information, thermodynamics, and potentially time itself. Black holes seem to encode information in a fundamentally different way than other physical systems an information theorist might observe. This suggests they might also process information, including temporal information, according to different rules. These unique information properties might be key to understanding whether closed time-like curves are physically possible. The holographic principle, the idea that all the information contained in a volume of space can be encoded on its boundary, emerged from studies of black hole thermodynamics. This principle suggests a duality between gravity in our universe and a quantum field theory on its boundary, potentially providing new mathematical tools for understanding extreme space-time geometries like those that might allow for time travel. While laboratory experiments cannot create actual black holes, they can produce analogues that mimic certain aspects of black hole physics. These artificial black holes, created in superfluids, optical systems, or electronic circuits, allow scientists to study phenomena like Hawking radiation in controlled laboratory settings. By creating these analog systems, an experimental physicist might explain, we can test theoretical predictions about black hole behavior that would otherwise be impossible to verify. While they don't reproduce all aspects of real black holes, they provide valuable insights into specific phenomena that might be relevant to understanding exotic effects like closed time-like curves. The ongoing search for a unified theory of physics, one that reconciles quantum mechanics with general relativity, remains central to understanding whether time travel through black holes could ever be possible. Various approaches, including string theory, loop quantum gravity, and causal set theory, offer different perspectives on the nature of space-time at the smallest scales and highest energies. These theories make different predictions about the interior structure of black holes and whether singularities truly exist as infinitely dense points where space-time breaks down completely. The resolution of the singularity question has profound implications for closed time-like curves and potential time travel, as many theoretical time travel scenarios involve passing near or through the central regions of black holes. While we await a complete theory of quantum gravity, each new observation and experiment provides another piece of the puzzle. The recent detection of gravitational waves, the imaging of black hole shadows, and precision measurements of relativistic effects on Earth all contribute to our understanding of the extreme physics where time travel might potentially occur. The practical challenges of studying black holes can't be overstated. These objects are incredibly distant, extremely compact, and surrounded by environments hostile to any form of direct exploration. While science fiction often imagines sending probes or even crewed missions to explore black holes up close, the reality is far more challenging. Even if we could somehow build a probe capable of surviving near a black hole, a space engineer might explain, the communication challenges would be enormous. Time dilation would make real-time communication impossible, and the extreme gravitational gradients would tear apart conventional materials long before they reached regions where exotic effects like closed time-like curves might occur. Despite these challenges, the theoretical investigation of black holes and their relationship to time continues to advance. Each new mathematical insight, astronomical observation, or laboratory experiment brings us closer to understanding whether these cosmic objects could ever serve as gateways through time. As we look to the future of this field, several key questions guide ongoing research. Can quantum effects near black hole horizons create pathways for information to travel backward in time? Do rotating black holes truly allow for stable closed time-like curves, as some solutions to Einstein's equations suggest? And perhaps, most fundamentally, does time itself emerge from more basic quantum processes, with black holes simply revealing its malleable nature more clearly than other cosmic phenomena? The answers to these questions lie at the intersection of our most advanced theories and observations. While time travel through black holes remains firmly in the realm of theoretical possibility rather than demonstrated reality, the scientific exploration of these possibilities continues to yield profound insights into the nature of time, space, and the universe we inhabit. Now, as we complete our survey of the real-world experiments and observations that inform our understanding of black holes and time, let's turn to an even more fundamental question: how quantum mechanics challenges our very conception of time itself. For it may be that the key to understanding time travel lies not in the macroscopic realm of black holes and relativity, but in the microscopic world of quantum physics, where time itself may emerge from deeper principles yet to be fully understood. While general relativity describes how massive objects like black holes warp the fabric of space-time, quantum mechanics governs the behavior of matter and energy at the smallest scales. These two pillars of modern physics offer dramatically different perspectives on the nature of reality, and nowhere do these differences become more apparent than in their treatment of time itself. As we explore the possibility of time travel through black holes, we must confront a profound question. What is time, really, according to quantum mechanics? In the realm of general relativity, time is woven into the fabric of space-time, a dimension that can stretch, contract, and curve in response to mass and energy. Black holes represent regions where this curvature becomes extreme, potentially allowing for closed time-like curves and the theoretical possibility of time travel. But quantum mechanics presents a very different picture of time, one that might fundamentally alter our understanding of whether time travel is possible, even in principle. In quantum mechanics, a theoretical physicist might explain, time appears as a parameter rather than an observable quantity. Unlike position or momentum, which are represented by operators in the mathematical framework of quantum theory, time enters the equations as an external parameter that flows uniformly forward. This creates an immediate tension with general relativity, where time is a dynamic part of space-time itself. This fundamental difference in how the two theories treat time lies at the heart of the ongoing effort to develop a theory of quantum gravity, a unified framework that would apply in extreme environments like the interiors of black holes, where both quantum effects and gravitational effects become significant simultaneously. The quantum view of time introduces several fascinating concepts that challenge our intuitive understanding of temporal flow. One of these is quantum superposition, the principle that quantum systems can exist in multiple states simultaneously until measured. In the famous thought experiment of Schrödinger's cat, a hypothetical feline is both alive and dead at the same time, existing in a superposition of states until an observation collapses this superposition into a single definite outcome. Applied to time, this principle raises a provocative question. Could events themselves exist in superposition, with multiple timelines coexisting until some cosmic measurement collapses them into a single history? Some interpretations of quantum mechanics suggest precisely this possibility, that the universe might exist in a superposition of different histories, each with its own timeline. The path integral formulation of quantum mechanics, developed by Richard Feynman, suggests that a particle traveling from point A to point B takes all possible paths simultaneously, a quantum physicist might tell you. Similarly, one could imagine the universe itself taking all possible historical paths simultaneously, existing in a quantum superposition of different timelines. This perspective aligns intriguingly with the many worlds interpretation of quantum mechanics, which we discussed earlier in the context of time travel paradoxes. If reality branches into multiple parallel timelines with each quantum event, then perhaps what we perceive as the flow of time is simply our consciousness traveling along one particular branch of an infinitely branching tree of possibilities. From this quantum perspective, time travel through black holes takes on a different character. Rather than moving backward or forward along a single timeline, a time traveler might be shifting between different branches of this quantum multiverse, experiencing what feels like time travel, but is actually navigation through parallel realities. Quantum entanglement, Einstein's spooky action at a distance, adds another layer of complexity to our understanding of time. When particles become entangled, their properties become correlated in ways that seem to transcend spatial separation. Measure one particle, and its entangled partner instantly assumes a corresponding state, regardless of the distance between them. Recent experiments have extended this concept into the temporal domain through what physicists call temporal entanglement. In these scenarios, quantum correlations seem to span time as well as space, with measurements in the present apparently connected to states in both the past and future. Temporal entanglement experiments suggest that quantum correlations don't just reach across space, but across time as well, a quantum optics researcher might explain. This doesn't allow for sending information backward in time. That would violate causality, but it does suggest that at the quantum level, time might be less rigid and linear than we experience it. These quantum correlations across time relate to another fundamental aspect of quantum mechanics, the measurement problem. In standard interpretations of quantum theory, It's the act of measurement that causes a quantum system to collapse from a superposition of possibilities into a definite state. This raises profound questions about consciousness, observation, and the nature of reality itself. Some theorists have proposed that consciousness itself might play a role in the collapse of quantum superpositions, an idea known as the von Neumann-Wigner interpretation. While controversial among physicists, this perspective raises fascinating questions about the relationship between mind, matter, and time. Could consciousness itself be the key to understanding the flow of time and the possibility of time travel? If consciousness plays a role in collapsing quantum possibilities into definite realities, a philosopher of physics might suggest, then perhaps our subjective experience of time, the sense that the present moment is somehow special and that time flows from past to future, reflects something fundamental about how consciousness interacts with quantum reality. These speculations take us far beyond established science, but they highlight the profound connections between quantum mechanics, consciousness, and our experience of time, connections that might ultimately bear on the possibility of time travel through black holes or other exotic means. More firmly grounded in mainstream physics is the concept of quantum decoherence, the process by which quantum systems interact with their environment, losing their delicate superpositions and beginning to behave more like the classical, intuitive world of our everyday experience. Decoherence explains why quantum weirdness remains hidden at macroscopic scales, despite governing the behavior of the particles that make up our world. Decoherence is like quantum amnesia, a physicist working on quantum computing might explain. As quantum systems interact with their surroundings, the delicate quantum information they contain leaks out into the environment, making quantum superpositions effectively impossible to detect or maintain in large objects. This process creates what we experience as the arrow of time, the apparent one-way flow from past to future. Quantum systems naturally evolve from ordered, coherent states to disordered, decohered ones, mirroring the increase in entropy described by the second law of thermodynamics. This quantum perspective suggests that the flow of time might emerge from the statistical behavior of countless quantum particles, rather than being a fundamental feature of reality. If time's arrow emerges from quantum decoherence, what does this imply for time travel? It suggests that reversing the flow of time would require reversing decoherence itself, essentially recohering quantum information that has spread throughout the environment. While theoretically possible according to the fundamental laws of physics, the practical challenges would be astronomical, requiring precise control over countless particles across vast regions of space. Quantum mechanics tells us that the laws of physics are time-symmetric at the fundamental level, a theoretical physicist might observe. The equations work equally well whether time runs forward or backward. It's only the statistical behavior of large collections of particles, the march toward greater entropy, that gives time its apparent direction. This perspective aligns with the block universe view suggested by relativity, where past, present, and future all exist with equal reality. In this view, the flow of time is something like an illusion, a product of our consciousness moving through a static, four-dimensional space-time. Quantum mechanics adds the wrinkle that this space-time might not be entirely deterministic, but probabilistic, with multiple possible futures existing in superposition. Near black holes, where general relativity predicts extreme distortions of space-time, quantum effects would presumably become significant as well. The event horizon of a black hole represents not just a boundary in space, but potentially a boundary in our understanding of physics itself, a region where quantum mechanics and general relativity must somehow be reconciled. Some approaches to quantum gravity suggest that space-time itself might emerge from more fundamental quantum processes, rather than being a basic feature of reality. In these theories, what we experience as time and space arises from the entanglement and interactions of quantum entities at a deeper level of reality. In certain quantum gravity approaches, space-time isn't fundamental but emergent, a researcher in loop quantum gravity might explain. Just as temperature emerges from the collective motion of atoms, what we experience as time might emerge from relationships between quantum events. Near a black hole, where space-time is severely curved, this emergent quality becomes more apparent. This notion of emergent time has profound implications for time travel. If time itself isn't fundamental but arises from deeper quantum processes, then time travel might require manipulating those underlying processes rather than simply moving backward or forward along a dimension of space-time. Perhaps black holes, where space-time breaks down entirely at the singularity, provide a window into this more fundamental level of reality. Theoretical approaches to quantum gravities offer various perspectives on what happens at the center of a black hole. The singularity, where general relativity predicts infinite density and curvature. String theory suggests that singularities might be resolved by the extended nature of fundamental strings, which can't be compressed beyond a certain size. Loop quantum gravity proposes that space-time itself has a discrete quantum structure that prevents true infinities from occurring. These approaches offer different visions of what might happen if we could somehow journey to the center of a black hole. Rather than encountering an infinite singularity, we might find a region where space and time, as we know them, dissolve into something more fundamental, perhaps providing pathways to other regions of space-time or even other universes entirely. The concept of information plays a crucial role in our quantum understanding of black holes and time. According to quantum mechanics, information can never be truly destroyed, a principle that comes into apparent conflict with the behavior of black holes, which seem to swallow information irretrievably when matter falls beyond the event horizon. This conflict, known as the black hole information paradox, has driven theoretical developments including Hawking radiation, the quantum process by which black holes slowly evaporate, potentially releasing the information they've absorbed. The resolution of this paradox has implications for understanding whether the apparent loss of information when crossing the event horizon of a black hole is reversible, a critical question for potential time travelers. If information that falls into a black hole is eventually returned to the universe through Hawking radiation, albeit in a highly scrambled form, a quantum information theorist might suggest, then perhaps the apparent one-way nature of crossing the event horizon isn't as absolute as classical general relativity suggests. This might open the door to theoretical possibilities for time travel that don't violate quantum principles of information conservation. Recent theoretical work on black hole information has led to the firewall paradox, a conflict between fundamental principles of quantum mechanics that arises when considering what happens at a black hole's event horizon. Different resolutions to this paradox suggest different pictures of what crossing the event horizon might be like, with implications for whether such a crossing could be part of a closed time-like curve that returns to its starting point in space-time. Some researchers have proposed that quantum entanglement across the event horizon might play a key role in resolving these black hole paradoxes. The idea that particles inside and outside the black hole remain quantum mechanically entangled challenges our classical notion of the event horizon as a one-way boundary and suggests a more nuanced quantum picture of black hole physics. For potential time travelers, these quantum considerations introduce both complications and possibilities. On the one hand, quantum uncertainty and the probabilistic nature of quantum mechanics might make precise navigation through time much more challenging than classical physics would suggest. On the other hand, quantum effects might provide loopholes in causality that classical physics doesn't allow, potentially enabling forms of temporal navigation that don't create paradoxes. The concept of the quantum vacuum, the seething background of virtual particles that continuously pop in and out of existence according to quantum principles, adds another dimension to our understanding of time near black holes. This quantum vacuum plays a key role in Hawking radiation and might influence the behavior of space-time itself in extreme gravitational environments. The quantum vacuum isn't truly empty, but filled with quantum fluctuations, virtual particles that briefly borrow energy to come into existence before disappearing again, a quantum field theorist might explain. Near a black hole's event horizon, these fluctuations can be amplified, with one virtual particle falling into the black hole while its partner escapes as real radiation. This process connects quantum mechanics directly to the macroscopic behavior of black holes. These quantum vacuum fluctuations might be relevant to understanding closed time-like curves as well. Some theoretical approaches suggest that quantum fluctuations would become increasingly significant near a closed time-like curve, potentially destabilizing it or preventing it from forming in the first place, an idea related to Hawking's chronology protection conjecture, which proposes that the laws of physics ultimately prevent time travel paradoxes. The tension between quantum mechanics and general relativity becomes most apparent in what physicists call the Trans-Planckian problem. As matter falls into a black hole, it eventually gets compressed to densities and energies that exceed the Planck scale, the regime where our current theories break down completely. At these scales, quantum effects on space-time itself become dominant, requiring a full theory of quantum gravity to describe what happens. Beyond the Planck scale, we simply don't know how space-time behaves, a quantum gravity researcher might acknowledge. It might become discrete rather than continuous, or develop foam-like properties, or transform in ways we can't currently imagine. These trans-Planckian effects would presumably be crucial for understanding whether closed time-like curves could exist in reality, rather than just in the mathematical solutions of classical general relativity. Some speculative approaches to quantum gravity suggest that time itself might dissolve at the Planck scale, with temporal relationships emerging only at larger scales. If this is the case, then the concept of time travel might need to be radically reconceived. Rather than moving backward or forward in time, a trans-Planckian traveler might exit the realm of time altogether, re-entering at a different point through processes that transcend our current understanding. The holographic principle, which we touched on earlier, provides another perspective on the relationship between quantum mechanics and time near black holes. According to this principle, all the information contained in a volume of space can be encoded on its boundary, like a three-dimensional image stored on a two-dimensional hologram. Applied to black holes, this principle suggests that all the information about what falls into a black hole might be encoded on its event horizon rather than truly passing inside. This perspective challenges our intuitive notion of the black hole interior as a region of space-time separate from the exterior, with implications for whether paths through the black hole interior could form closed loops in time. If the holographic principle is correct, a string theorist might tell you, then what we think of as inside the black hole may be a kind of illusion, a complementary description of information that's actually encoded on the event horizon itself. This wouldn't make black holes any less real, but would transform our understanding of their internal structure and whether that structure could support time travel. Even more exotic is the possibility that quantum mechanics might allow for retrocausality, the idea that events in the future might influence the past through quantum correlations. While mainstream physics maintains that information can't travel backward in time, some interpretations of quantum experiments, like the delayed choice quantum eraser, suggest a more nuanced view of temporal causality than our classical intuitions allow. If retrocausality is possible at the quantum level, this might provide yet another perspective on time travel, one where information, rather than physical objects, moves through time, influencing the past in subtle ways that don't create logical paradoxes. Quantum computing researchers have shown theoretically that quantum computers with access to closed time-like curves could solve problems even more efficiently than ordinary quantum computers, suggesting practical applications for temporal loops if they could be harnessed. Throughout this exploration of quantum mechanics and time, a common theme emerges. The universe at its most fundamental level may be far stranger, more interconnected, and less bound by our intuitive notions of time than classical physics suggests. While we don't yet know whether time travel through black holes or any other means is physically possible, the ongoing revolution in our understanding of quantum reality continues to expand the horizons of what we can imagine. Quantum mechanics has repeatedly forced us to abandon cherished intuitions about how reality works, a quantum foundations researcher might observe. From wave-particle duality to quantum entanglement to the measurement problem, quantum theory challenges us to think beyond the constraints of our everyday experience. Time travel may ultimately prove impossible, but if so, the reasons will likely emerge from quantum principles rather than classical ones. As we continue to probe the mysteries of quantum mechanics and its relationship to gravity and time, each discovery brings us closer to understanding whether black holes could ever serve as gateways through time. While definitive answers remain elusive, the journey itself reveals profound insights about the nature of reality and our place within it. Looking ahead to the future of this research, new experimental approaches and theoretical frameworks promise to shed additional light on these fundamental questions. From quantum simulations of black hole physics to increasingly precise tests of quantum entanglement across time, scientists continue to push the boundaries of what we can know about the quantum nature of time itself. As we conclude our exploration of quantum mechanics and time, let's turn our attention to the future of time travel research. What emerging theories and technologies might bring us closer to understanding whether time travel through black holes could ever move from theoretical possibility to practical reality? And what would the implications be for our understanding of the universe and our place within it if we discovered that time travel was fundamentally possible or fundamentally impossible? As we stand at the frontier of our scientific understanding, the question of time travel through black holes remains tantalizingly open. While current technology and theory don't provide definitive answers, ongoing research continues to push the boundaries of what we know and what might be possible. From theoretical breakthroughs to technological innovations, the coming decades promise to transform our understanding of time travel from science fiction fantasy to scientifically grounded possibility, or perhaps to conclusively demonstrate its impossibility. Either outcome would profoundly reshape our understanding of the universe and our place within it. The work of contemporary theoretical physicists like Kip Thorne, who served as scientific consultant for the film Interstellar, exemplifies the rigorous approach modern science brings to questions once relegated to speculation. Thorne's research on traversable wormholes, theoretical tunnels through space-time that might allow for rapid transit across vast cosmic distances or even through time itself, represents one of the most promising avenues for potential time travel research. What's remarkable about Thorne's work, a theoretical physicist might tell you, is how it transformed the conversation around wormholes from pure speculation to rigorous mathematical physics. By identifying the specific conditions under which wormholes might remain stable and traversable, including the requirement for exotic matter with negative energy density, Thorne established a clear research agenda for those interested in the possibility of time travel. This research agenda includes both theoretical and experimental components. On the theoretical front, physicists continue to refine mathematical models of wormholes and other exotic space-time structures, exploring whether quantum effects near these structures might ameliorate some of the challenges identified in classical general relativity, such as the need for physically unrealistic amounts of exotic matter. Recent theoretical work has focused on the quantum energy teleportation protocol, a mechanism by which negative energy might be effectively teleported from one location to another through quantum correlations. While still highly speculative, this approach suggests that the exotic matter needed to stabilize a wormhole might be generated through quantum effects, rather than requiring new forms of matter with inherently negative energy. The exotic matter requirement has long been seen as the most significant obstacle to traversable wormholes, a quantum gravity researcher might explain. If quantum energy teleportation or similar quantum effects could provide the negative energy needed, that would represent a major breakthrough in making wormholes theoretically viable. Experimental research, meanwhile, focuses on testing underlying principles relevant to potential time travel mechanisms. While we can't yet create or detect actual wormholes or closed time-like curves, scientists can test related aspects of general relativity and quantum mechanics that bear on the question of time travel. The ongoing development of quantum technologies promises to enable increasingly sophisticated tests of quantum mechanics in regimes relevant to time travel research. Quantum computing, in particular, may soon allow for simulations of quantum systems complex enough to model aspects of black hole physics and potential time travel scenarios. Quantum computers leverage principles like superposition and entanglement to perform calculations impossible for classical computers, a quantum computing researcher might explain. As these technologies mature, they could allow us to simulate the behavior of quantum fields in curved spacetime, potentially revealing whether quantum effects near black holes might enable or prevent closed time-like curves. Some researchers have even proposed using quantum computing to test specific aspects of time travel physics directly. Theoretical work suggests that a quantum computer with access to closed time-like curves could solve certain problems exponentially faster than even an ordinary quantum computer. While actual closed time-like curves remain speculative, these theoretical results provide concrete predictions that could be tested if such curves were ever found or created. Advanced gravitational wave observatories represent another promising technological development for time travel research. While current observatories like LIGO and Virgo have already revolutionized our understanding of black holes, next-generation detectors promise even greater sensitivity and broader frequency coverage, potentially revealing subtle effects in the gravitational waves emitted by black holes that might bear on the possibility of closed time-like curves. The proposed Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2034, will detect gravitational waves at frequencies impossible to observe from Earth. This space-based observatory could potentially observe the mergers of supermassive black holes across the universe, providing unprecedented insights into the behavior of space-time under the most extreme conditions known to physics. With LISA and other advanced gravitational wave observatories, an astrophysicist might predict, we'll be able to probe the detailed structure of spacetime near black holes with incredible precision. We might detect signatures of frame dragging and other effects that play key roles in theoretical models of time travel through rotating black holes. Astronomical observations at other wavelengths continue to advance as well. The development of 30-meter class optical telescopes and sensitive radio interferometers promises direct imaging of the environment around black holes with unprecedented resolution. These observations will test theoretical models of black hole physics with greater precision than ever before, potentially revealing subtle effects relevant to the possibility of closed time-like curves. We're entering a golden age of black hole astronomy, an observational astrophysicist might tell you. With each new observatory and each new observation technique, we peel back another layer of the mystery surrounding these extreme objects. Whether or not time travel proves possible, these observations will transform our understanding of how spacetime behaves in the most extreme environments in the universe. Laboratory experiments in quantum optics and related fields continue to probe the nature of time at the quantum level. While these experiments can't directly test macroscopic time travel, they can explore quantum phenomena that challenge our conventional understanding of temporal ordering and causality. Recent experiments have demonstrated quantum entanglement across significant time intervals, suggesting that quantum correlations might transcend our ordinary notion of temporal sequence. While these effects don't allow for sending information backward in time, in a way that would violate causality, they hint at a more complex relationship between quantum systems and time than classical physics would suggest. What's fascinating about these quantum experiments, a quantum optics researcher might observe, is how they blur the lines between past, present, and future at the quantum level. While we don't yet know whether these effects could ever scale up to enable macroscopic time travel, they certainly challenge our intuitive notion of time as a simple, linear flow from past to future. The development of metamaterials, engineered substances with properties not found in natural materials, represents another technological frontier relevant to time travel research. While these materials can't create actual closed time-like curves, they can manipulate the flow of light and other waves in ways that mimic certain aspects of curved spacetime. Transformation optics allows us to create materials that bend light around objects, effectively making them invisible, a metamaterials engineer might explain. Similar principles might eventually allow us to create laboratory analogues of exotic space-time geometries, providing insights into how light and matter would behave near a wormhole or time-like curve without actually creating those extreme conditions. Advances in particle physics, particularly in our understanding of quantum field theory in curved spacetime, continue to refine our models of how matter and energy behave near black holes. The ongoing development of quantum field theory techniques allows for increasingly precise calculations of quantum effects in strong gravitational fields, potentially revealing whether these effects would permit or prevent closed time-like curves. Quantum field theory in curved spacetime represents the current best approximation to a full theory of quantum gravity, a theoretical physicist might explain. By applying these techniques to models of rotating black holes and other exotic spacetime structures, we can make predictions about whether quantum effects would stabilize or destabilize potential time machines. The search for a full theory of quantum gravity remains one of the great outstanding challenges in theoretical physics. Various approaches, including string theory, loop quantum gravity, and causal set theory, offer different perspectives on how gravity and quantum mechanics might be reconciled at the most fundamental level. Each of these approaches makes different predictions about the nature of spacetime at the smallest scales and under the most extreme conditions. Predictions that have profound implications for the possibility of time travel. Some approaches suggest that spacetime itself emerges from more fundamental quantum processes, potentially allowing for connections between different regions of spacetime that might appear as time travel from our macroscopic perspective. In certain quantum gravity approaches, what we experience as the flow of time might be a macroscopic approximation of something much more complex at the fundamental level, a quantum gravity researcher might suggest. This emergent view of time opens new possibilities for understanding how regions of spacetime might connect in ways that aren't obvious from our classical perspective. Theoretical exploration of black hole horizons continues to yield insights into the nature of time in these extreme environments. Recent work on soft hair, subtle quantum characteristics that might be imprinted on black hole horizons, suggests that black holes might preserve more information about what falls into them than previously thought, with implications for whether the apparent one-way nature of horizon crossing is absolute. The discovery that black holes might carry more information on their horizons than we previously believed challenges the simple picture of black holes as objects from which nothing can escape, a black hole theorist might explain. This more nuanced view might eventually reveal pathways for information and possibly other things to effectively transit a black hole without being irretrievably lost. Advanced computer simulations of black holes and other exotic spacetime structures provide another tool for exploring time travel possibilities. As computing power continues to grow, these simulations can model increasingly complex scenarios involving strong gravity and quantum effects, potentially revealing configurations that might allow for closed time-like curves or demonstrating their impossibility. Modern numerical relativity techniques allow us to solve Einstein's equations in situations where analytical solutions are impossible, a computational physicist might tell you. As these techniques incorporate more quantum effects, we'll be able to explore regimes where both general relativity and quantum mechanics are important, precisely the regimes where time travel might be possible. The development of artificial intelligence and machine learning offers yet another avenue for time travel research. These technologies can analyze complex datasets and identify patterns that might elude human researchers, potentially revealing subtle signatures in astronomical observations or experimental data that bear on the question of time travel. Machine learning algorithms excel at finding patterns in high-dimensional data, an AI researcher with interests in physics might explain. Applied to gravitational wave observations or black hole imaging data, these algorithms might identify signatures of exotic spacetime structures that human analysts would miss, potentially revealing evidence relevant to the possibility of closed time-like curves. Some researchers have proposed more speculative approaches to time travel research, including searching for evidence of visitors or signals from the future. While highly controversial within mainstream physics, These approaches ask whether advanced civilizations with time travel capabilities might have left detectable traces in the present era. Proposed detection methods include searching for technological artifacts with anachronistic properties or monitoring for signals specifically designed to be detectable by future civilizations. While most physicists remain skeptical of such approaches, they represent attempts to bring empirical methods to bear on the question of time travel even before we fully understand its theoretical basis. If time travel to the past is ever developed in the future history of our civilization, a speculative researcher might suggest, then perhaps we should expect to find evidence of time travelers or their influence in our present era. The absence of such evidence might itself be significant, suggesting either that time travel to the past remains forever impossible, or that it operates under constraints that prevent noticeable interference with history. The philosophical implications of time travel research extend beyond physics into metaphysics, ethics, and our understanding of human nature. If time travel proved possible, how would it transform our conception of free will, causality, and moral responsibility? If it proved definitively impossible, what would that tell us about the fundamental structure of reality? The quest to understand whether time travel is possible is ultimately about more than just physics, a philosopher of science might observe. It's about understanding the nature of time itself, whether the past and future exist in the same sense as the present, whether causality is absolute or relative, and whether the universe unfolds according to fixed laws or contains elements of genuine indeterminacy. For the average person, the practical implications of time travel research might seem remote, but the insights gained from this exploration have already transformed our understanding of the universe. From the confirmation of gravitational waves to the imaging of black hole shadows, the pursuit of these fundamental questions has yielded concrete advances in our knowledge of the cosmos. Even if time travel through black holes ultimately proves impossible, the journey of exploration will have been worthwhile. As with many scientific quests, the value lies not just in reaching the destination, but in what we discover along the way. Each step toward understanding whether time travel is possible brings us closer to comprehending the true nature of time, space, and our universe. The history of science teaches us that investigating seemingly impossible questions often leads to unexpected breakthroughs. A historian of science might remind us, when Einstein developed general relativity, he wasn't explicitly trying to enable time travel, yet his theory raised that possibility in a scientifically rigorous way for the first time. Similarly, today's research into quantum gravity and black hole physics might yield applications we can't currently imagine, regardless of whether time travel itself proves possible. Looking ahead to the coming decades, several key research directions promise to advance our understanding of potential time travel through black holes. The continued development of quantum gravity theories will refine our understanding of space-time at the most fundamental level, potentially revealing whether closed time-like curves can exist in a full quantum treatment of gravity. Advanced astronomical observations will probe the environments around black holes with unprecedented precision, testing theoretical models and potentially revealing signatures of exotic physics. Laboratory experiments will test quantum effects relevant to time travel at increasingly macroscopic scales, exploring the boundaries between quantum and classical behavior of time. Theoretical work will continue to explore the implications of existing physical theories for time travel, identifying key constraints and possibilities within our current understanding. Computational approaches will model increasingly complex scenarios involving strong gravity and quantum effects, simulating potential time travel configurations and their stability. The next few decades will be transformative for our understanding of black holes and their relationship to time, a researcher in the field might predict. While we may not achieve actual time travel within that time frame, or perhaps ever, we will certainly develop a much deeper understanding of whether it's possible in principle and what constraints the laws of physics place on potential time machines. As we reach the frontier of our current knowledge, we find ourselves confronting questions that touch on the deepest mysteries of existence. Is time a fundamental feature of reality, or does it emerge from more basic principles? Are past and future as real as the present? Or do they exist only as possibilities and memories? Could advanced civilizations someday navigate through time as we now navigate through space? These questions may seem philosophical, but they have concrete implications for the physical possibility of time travel through black holes or other means. As our understanding advances, some possibilities will be ruled out while others gain support, gradually shifting time travel from the realm of pure speculation toward either demonstrated possibility or demonstrated impossibility. Whichever direction the evidence ultimately leads, the journey promises to transform our understanding of the universe and our place within it. By probing the limits of what is possible, we come to better understand what is, the true nature of time, space, and reality itself. The quest to understand whether time travel is possible represents science at its most ambitious and profound, a theoretical physicist might conclude. It forces us to confront the deepest questions about the nature of time and causality, pushing our theories to their limits and beyond. Whether time travel ultimately proves possible or not, the pursuit itself expands the horizons of human knowledge and inspires us to look at the universe with fresh eyes. As we conclude our exploration of the future of time travel research, let's step back and reflect on the journey we've taken through the physics of black holes and time. From the basic principles of general relativity to the exotic possibilities of quantum gravity, from thought experiments to cutting-edge observations, we've traversed the landscape of modern physics in search of answers to one of humanity's most enduring questions. Can we travel through time? The answer, for now, remains open. A frontier of knowledge waiting to be explored by current and future generations of scientists, philosophers, and curious minds of all kinds. What discoveries await them, and what transformations in our understanding of reality might those discoveries bring? Only time will tell. After our journey through the physics of black holes, the nature of time, and the frontier of scientific research, we return to our original question: is time travel through black holes possible? The answer, like many profound questions in science, isn't a simple yes or no. It resides in the nuanced realm where theoretical possibility meets practical limitations, where mathematical solutions encounter physical constraints, and where our understanding remains incomplete but ever-evolving. Let's consider what we've learned. General relativity, Einstein's revolutionary theory of gravity, provides the mathematical framework for understanding black holes. This same theory permits solutions like closed, time-like curves that would theoretically allow for time travel under certain conditions. Rotating black holes, described by the Kerr metric in general relativity, create environments where space-time becomes so severely twisted that paths looping back through time become mathematically possible. The mathematics is clear, a theoretical physicist might tell you. General relativity doesn't prohibit closed time-like curves in principle. What remains uncertain is whether the specific conditions required for these curves could ever exist in our physical universe, given the constraints of other physical laws and principles. Those constraints are significant. Creating a traversable wormhole or a stable closed time-like curve would likely require exotic matter with negative energy density, a form of matter that violates what physicists call the energy conditions that seem to govern our universe. While quantum effects can create small amounts of negative energy density in limited regions of space, scaling this up to the levels needed for macroscopic time travel presents enormous challenges. Quantum mechanics introduces additional complications. The probabilistic nature of quantum physics conflicts with the deterministic character of closed time-like curves, creating paradoxes that may indicate fundamental incompatibilities between time travel and the quantum nature of our universe. Stephen Hawking's chronology protection conjecture suggests that the laws of physics might ultimately conspire to prevent time travel and the logical paradoxes it would introduce. When we try to combine quantum mechanics with general relativity in regimes where both are important, like near black hole singularities, our current theories break down, a quantum gravity researcher might explain. This breakdown might ultimately rule out time travel, or it might reveal new possibilities we haven't yet imagined. Until we have a complete theory of quantum gravity, the question remains open. Real-world observations provide both tantalizing hints and sobering constraints. We've confirmed that black holes exist and that they can rotate rapidly, creating frame-dragging effects predicted by general relativity. We've detected gravitational waves from black hole mergers and captured images of supermassive black holes. These observations validate the theoretical framework that makes time travel conceivable, but they also highlight the extreme conditions involved. The environments near black holes are among the most hostile in the universe, an astrophysicist might caution. Intense gravitational gradients would tear apart conventional matter long before it reached regions where time travel might be possible. The radiation environment would be lethal to any unprotected biological organism. These practical challenges may prove as limiting as any theoretical constraints. If time travel through black holes is possible, it would likely require technology far beyond our current capabilities. A civilization thousands or millions of years more advanced than our own might develop methods to survive near black holes, to manipulate exotic matter, or to navigate the quantum complexities of closed time-like curves. Such capabilities remain in the realm of speculation rather than near-term possibility. The distinction between what is theoretically possible and what is practically achievable runs through our entire exploration. Just as the laws of aerodynamics don't prohibit human flight, but do impose constraints that shaped how we ultimately achieved it, the laws of physics might allow time travel while imposing constraints that shape what form it could possibly take. If time travel through black holes ever proved possible, it would likely look very different from the intuitive notion of stepping into a machine, setting a date, and emerging in the past or future. It might involve quantum information rather than physical objects, microscopic effects rather than macroscopic transport, or forms of temporal connection we haven't yet conceived. Throughout the history of science, reality has often proved stranger and more fascinating than our initial conceptions. A philosopher of science might observe, if time travel is possible, it may emerge in forms that transcend our current imagination, just as quantum mechanics and relativity transcended the classical physics that preceded them. Even if practical time travel remains forever beyond our reach, the theoretical exploration of its possibility continues to drive scientific progress. The questions raised by potential time travel through black holes touch on the deepest aspects of physics, the nature of time itself, the relationship between quantum mechanics and gravity, the fundamental structure of space-time. Pursuing these questions leads to new insights regardless of whether time travel itself proves possible. The quest to understand black holes and their relationship to time exemplifies science at its most profound. It pushes us beyond common sense into realms where intuition fails and only mathematics can guide us. It challenges us to consider possibilities that seem impossible by everyday standards, but emerge naturally from our best physical theories. And it reminds us that the universe may be stranger, more complex, and more wondrous than we can readily imagine. For the foreseeable future, time travel through black holes remains in the liminal space between science fiction and scientific possibility, neither conclusively ruled out nor clearly achievable. This uncertainty itself is valuable, defining a frontier of knowledge where theoretical physics, observational astronomy, experimental science, and philosophical inquiry converge. The most exciting phrase to hear in science, physicist Richard Feynman once observed, is not eureka, but that's funny. The peculiar possibilities of time travel through black holes represent just such a moment, an anomaly that emerges from our theories, challenging us to either explain it away or transform our understanding to accommodate it. As our scientific journey continues, new observations, experiments, and theoretical insights will gradually clarify whether time travel through black holes could ever transition from mathematical possibility to physical reality. Gravitational wave observatories will detect more black hole mergers, providing unprecedented data about these extreme objects. Advanced telescopes will image black holes with greater precision, revealing the detailed structure of space-time in their vicinity. Quantum experiments will probe the foundations of time and causality at increasingly macroscopic scales. Meanwhile, theoretical work in quantum gravity will continue to advance, potentially resolving the tensions between general relativity and quantum mechanics that currently cloud our understanding of what happens in the most extreme gravitational environments. This work may eventually provide a definitive answer about whether closed time-like curves can exist in a universe governed by the complete laws of physics, not just the approximation provided by general relativity. While we await these advances, the possibility of time travel through black holes remains a source of wonder and inspiration, a reminder of how much remains to be discovered about the universe and its fundamental laws. It invites us to stretch our imaginations, to question our basic assumptions, and to recognize the vast territories of knowledge that lie beyond our current understanding. The universe is not only stranger than we imagine, physicist Arthur Eddington famously remarked, it is stranger than we can imagine. Black holes epitomize this strangeness, challenging our most basic intuitions about space, time, and causality. Whether or not they ultimately provide pathways through time, they certainly provide windows into the profound mystery at the heart of our cosmos. For those drawn to contemplate these mysteries, the journey itself is rewarding regardless of the destination. The questions raised by potential time travel through black holes connect to humanity's ancient fascination with time, our desire to revisit the past, to glimpse the future, to transcend the temporal constraints that define our existence. While we might never achieve physical time travel, the intellectual journey enriches our understanding of reality and our place within it. As we look to the stars and contemplate the black holes that populate our universe, from stellar remnants to the supermassive giants at the centers of galaxies, we're engaging with one of science's greatest adventures, the quest to understand the fundamental nature of space, time, and reality itself. This quest continues, driven by human curiosity, creativity, and our innate desire to explore the unknown. So is time travel through black holes possible? The honest answer is that we don't yet know with certainty. The mathematics of general relativity suggests it might be. Other physical principles suggest significant constraints. What we can say with confidence is that black holes continue to be among the most fascinating objects in our universe, cosmic laboratories where the laws of physics are tested to their limits. Whether or not they ever serve as gateways through time, black holes certainly serve as gateways to deeper understanding, challenging us to develop more complete theories, more precise observations, and more profound conceptual frameworks for understanding the cosmos. In this ongoing pursuit, the journey of discovery continues, with each answer revealing new questions and each insight opening new horizons of possibility. As you gaze up at the night sky, consider that among the stars visible to your naked eye, many will eventually collapse to form black holes. Others orbit around the supermassive black hole at the center of our galaxy. These cosmic objects, once merely theoretical curiosities, are now known to be fundamental components of our universe, shaping the evolution of galaxies, generating gravitational waves that ripple through space-time, and challenging our understanding of physics at its most fundamental level. The story of black holes and their relationship to time is still being written, with each new observation and theoretical breakthrough adding another chapter. While we may never send a physical traveler through a black hole to explore distant times, our scientific exploration allows us to voyage through the cosmos with our minds, transcending the limitations of our physical existence to comprehend the vastness and wonder of our universe. This intellectual journey stands among humanity's greatest adventures, a quest not for conquest or material gain, but for understanding. It connects us to the cosmos in profound ways, reminding us that the atoms in our bodies were forged in ancient stars, that the laws of physics that govern distant black holes also govern our daily existence, and that our capacity for curiosity and wonder is itself one of the universe's most remarkable creations. Some might wonder whether we should pursue time travel at all, given the philosophical and ethical questions it raises. If we could travel to the past, would we be tempted to alter history in ways that might have unpredictable consequences? If we could visit the future, Would knowledge of what awaits us rob us of the uncertainty that gives life much of its meaning and excitement? These questions have no easy answers, but they remind us that scientific advancement always carries with it philosophical implications that extend beyond the laboratory. The pursuit of knowledge about time travel isn't just a scientific question, but a deeply human one, a philosopher might reflect. Throughout history, humans have been fascinated by time, its apparent one-way flow, our inability to recapture the past or skip ahead to the future. This fascination reflects something fundamental about the human condition, our awareness of mortality, our desire to transcend limitations, our capacity to imagine possibilities beyond our immediate experience. Time travel through black holes lies at the intersection of our most advanced scientific theories and our most ancient human longings. It represents both the cutting edge of theoretical physics and the timeless human desire to break free from temporal constraints. This intersection of science and human aspiration gives the question of time travel a resonance that purely technical problems lack. Even as we pursue these profound questions, it's worth remembering that our understanding of black holes is itself relatively recent. Just a century ago, these objects were merely mathematical curiosities emerging from Einstein's equations. Today, we have photographed their shadows, detected the gravitational waves from their collisions, and mapped the orbits of stars around the supermassive black hole at the center of our galaxy. This rapid progress reminds us how quickly our understanding can advance, and how concepts that once seemed purely theoretical can become observational realities. The history of black hole physics teaches us intellectual humility, a historian of science might observe. Many times, what seemed impossible became possible. What seemed purely theoretical became observable. This history suggests caution in declaring any possibility, including time travel, permanently beyond reach. The study of black holes and potential time travel also highlights the deeply interconnected nature of our universe. The same physical laws that govern these exotic cosmic objects also apply to our everyday world. The time dilation effects that become extreme near black holes also affect satellites in orbiting Earth, requiring corrections to maintain accurate positioning. The quantum fluctuations that might play crucial roles in black hole physics also influence the behavior of electronic components in our computers and smartphones. This interconnectedness reminds us that we aren't separate from the cosmos, but an integral part of it. The atoms in our bodies were forged in ancient stellar explosions. The laws of physics that we discover apply universally, from the smallest subatomic particles to the largest supermassive black holes. Our capacity to comprehend these laws, to formulate mathematical models of reality, and to test these models through observation and experiment represents one of the most remarkable features of our universe. The emergence of consciousness capable of understanding the cosmos that created it. When we contemplate black holes and their relationship to time, an astrobiologist might suggest, we're really contemplating our own relationship to the universe. We're asking how the same laws that create these extreme objects also created the conditions for life and consciousness to emerge. We're tracing our cosmic heritage back to the fundamental structures of reality itself. Perhaps the most profound implication of our exploration is the recognition that time itself may be more complex, more malleable, and more mysterious than our everyday experience suggests. Both general relativity and quantum mechanics challenge our intuitive notions of time in different ways. Relativity by revealing its connection to space and its dependence on motion and gravity. Quantum mechanics by suggesting connections across time through entanglement and other quantum correlations. These scientific perspectives resonate with insights from philosophy, literature, and various cultural traditions that have long suggested alternative ways of conceptualizing time. From Eastern philosophical traditions that emphasize cyclical time to the eternal now, described by mystics across cultures, humans have repeatedly intuited that our everyday experience of time as a simple, linear flow might not represent its fundamental nature. The physics of black holes and potential time travel, a comparative philosopher might observe, offers scientific language for concepts that human cultures have explored through other means for millennia. The convergence of these different approaches to understanding time suggests we're touching something fundamental about reality, approaching it from different angles, but encountering the same underlying mystery. As we continue to explore these mysteries, we do so as part of a great human adventure that spans generations and transcends cultural boundaries. From ancient astronomers tracking the motions of planets, to medieval Islamic scholars developing mathematical techniques, to modern physicists formulating theories of quantum gravity, the quest to understand the cosmos represents one of humanity's noblest pursuits, an expression of our curiosity, creativity, and desire to comprehend our place in the vast universe we inhabit. The possibility of time travel through black holes, whether it ultimately proves achievable or remains forever theoretical, reminds us of the vast territories of knowledge that still await exploration. It humbles us by revealing the limits of our current understanding, while simultaneously inspiring us to push beyond those limits. It connects us to both the deepest mysteries of the cosmos and the most profound questions of human existence. The most beautiful experience we can have, Einstein once remarked, is the mysterious. It is the fundamental emotion that stands at the cradle of true art and true science. The mysteries of black holes, time, and potential time travel epitomize this beautiful experience, challenging us to expand our minds, to question our assumptions, and to glimpse the profound wonder that lies at the heart of reality. As we conclude our journey through the physics of black holes and time travel, we invite you to continue exploring these fascinating frontiers of knowledge. The adventure is ongoing, with new discoveries and theoretical breakthroughs emerging regularly. By engaging with these questions, you participate in one of humanity's greatest collective achievements, the ever-expanding understanding of our cosmic home and our place within it. Whether time travel through black holes ever becomes a physical reality or remains a theoretical possibility, the exploration itself enriches our lives and expands our horizons. It reminds us that the universe is more extraordinary than we might have imagined, and that our capacity to comprehend it is one of the most remarkable features of human existence. The next time you look up at the night sky, remember that among those distant points of light are black holes of various sizes, from stellar remnants to supermassive giants. These cosmic objects, once purely theoretical, are now known to be fundamental components of our universe. They shape galactic evolution, generate gravitational waves, and challenge our understanding of physics at its most fundamental level. They also, perhaps, hold keys to understanding the nature of time itself, and whether we might someday find ways to navigate through its mysterious depths. The story continues, and each of us, in our own way, contributes to its unfolding. Through our curiosity, our questioning, and our wonder at the cosmos, we participate in humanity's ongoing journey of discovery, a journey that has taken us from our first upward glances at the night sky to the edge of black holes, and perhaps, someday, beyond the conventional boundaries of time itself.